All right, everybody. Vignesh is also lolling. I missed something huge. Hi, good morning, good night. Good 24-hour cycle wherever you are. Oh, I see. That's funny. Well, might as well. Okay. Ah, so uh, there's a new flower arrangement for today. It's a little ikebana, a little Japanese contribution. Oh, thank you. Cool. I appreciate it. Okay. Everyone's waiting for it. This is sweet. I made this last night. A little cradle. It's called a crescent arrangement. Literally, nighttime is my time. Gosh darn it. Okay, so on this, by the way, on a piece of paper, it's a little bent. You can see. Thank you, guys. So let's start. Okay, we got some fun things. Sequel, a little bit more sequel. TM. Yeah, the gulab jamuns are away. I can put it back. Send it to you. Okay. So the homework went well for everybody, which is great. All kinds of questions on Piazza, just nice. So you see that illustrates something very important. You can hear me talk, look at ER diagrams, and understand most of it. But when you actually go do it, the devil is in the details, right? There's all kinds of schema, questions. How do I denote this? And what happens if I have two tables that share a key? Can I have two different foreign keys? On and on. But that's very cool, though. We will try and make accommodations, okay, Kevin, in case people are genuinely delayed. Also, last night, power was out, so at least one student was affected near the USC campus. We're pretty forgiving, by the way, so we hope, basically, um, do the right thing by trusting you, so we don't think that you abuse your privilege on purpose and lie and just say, oh, sorry, the power went out. I think you guys are better than that. So if you are late by, a few minutes sometimes because the server, just like died or whatever, as long as things are reasonable, like your excuses, your reasons, we will go with them. So don't worry about actual, genuine things that happen. The router turned off, anything at all. We'll accommodate. We'll make it work. Okay, we're not too strict and cruel. But check this out, though. This is very interesting. So if I put this up, 5 megs, just as simple as 5 megs of data back in the day. 62,000 cards. Okay, so it's almost as tall as her. All that. All that was just 5 meg. Yeah, it is wild. These days, a single image that you take, with your, megapixel camera is way more than 5 meg. But that's how many it took. Stack of cards. 4 days to load. This is the most insane part. So someone wrote a Fortran program, or maybe the Fortran program is like only here, this all data. Yeah, they look like they used to make dollars for IBM. Yeah, so if the program was this big and the rest was all data, they're trying to calculate the trajectory for a missile or something. It takes 4 days just to load the software, and then for the mainframe to run. 1966. Then along comes the hard drive. Like 10 years ago, they invented the hard drive, and the hard drive is the size of a refrigerator. It pretty much takes like all these people, to move it. 5 meg. Oh my God. So these days, a terabyte. So a quick question for you. How many times 5 meg is 1 terabyte? So what is the multiplication factor from 5 meg to 1 terabyte? And the shrinkage, this is about the size of fingertip. Wow. Yeah, that's the right answer. Exactly. It's 200,000, right? Because a terabyte is like 1,000 gigabytes. So you can take the 1,000 out. So pretend this is 1 giga, which is basically 1,000 meg. So this is, 200. So 5 times 200 and then times another 1,000. So 200,000. Wow. 200,000. Oh my God. That's the shrinkage that we get. And this is all relevant to data, by the way, because these days we think nothing of using a terabyte, drive like this. But in the future, you have bigger words such as petabyte, exabyte, yottabyte. And so we're going to get even more data from more devices, and we just don't know what to do at this point. Like, wow, what the hell? So we'll be at a point when it'll take our data 4 days to load. Yeah, it's actually called yotta, or like a YOTTA, yottabyte. Yeah, these are insanely large numbers that we just cannot comprehend. Like, wow. But then it's coming, meaning we're going to get data that is that big. So we need storage that big. And then more importantly, algorithms that still somehow process all the data fast. Otherwise, we'll look like the 4-day people. Oh, yeah. So one last thing, by the way, speaking about all that. This is SQL related, right? So there was a joke, I think I said last time, because somebody said, why learn all the SQL? And then I said, well, the machine's coming to take it away. So GPT-3 is what is called a pre-trained language model. By the way, this is not even the latest. That has 200 billion like parameters. So after that, Google has a 1 trillion parameter model. And a few days ago, they actually like released it for open source. It is wild. So what, Google just gives it away. But almost nobody in the world would have the capacity to actually run it. That's a different matter altogether. But these are huge, massively huge things that the world never imagined. Okay, so with GPT-3, if you can get your hands on it, right? This is what you can do, believe it or not. So from 423, it does basically like lots and lots of things. It's a natural language, like a system ultimately.
This is Jim. Jim works for a technology company that develops enterprise software.
Okay, so watch this.
When you hang around programmers, you might have heard about APIs, how they can be used to perform certain tasks or retrieve some data. But what are these exactly, and why were they created? Let me explain the problem with a simple, non-IT related example.
Interesting. I don't think it's the one that I wanted.
Public holiday APIs.
Wow.
APIs are all
Never
around.
Mind.
You've
Well, that's funny. I actually put the wrong thing in, but this. Wow. Okay, I'll tell you what.
And that brings us to the final use
We can still very easily just do this, okay? You can just say, actually, I'll search it here. Watch this. I'll just say GPT-3 SQL, okay? I think that should find it. GPT-3 SQL. That's a crazy connection between those two. Like, what the hell? Yeah, this one. So even the title, GPT writes my SQL queries for me. That's actually scary. This is a different one from what I told you, but it doesn't matter, okay? It's even shorter. Look at that. Okay, so this is what every manager wants, right? Like how many, medical patients have I had since the past 4 years. So then it's actually going to start to give you actual SQL. Okay, the system can output it. This one is not GPT-3, by the way, it's some other system. But look at that, that's a pretty simple query, right? That is how they all start. So it can now do more complex joins, but gradually if you train these things more and more, okay? So GPT-3 can be trained. So you would actually give a query and then also tell it in English, like what the query is like, and then use it like training, do it a few thousand different samples. And then it starts to figure out the pattern between the actual SQL and what you're asking in plain English. And then you can flip it. So then you can ask, and then it can output the SQL code. And it looks pretty damn good. And like I said, we're just starting out with this. So this is, kind of scary thing where unless you are, hotshot, amazing SQL programmer, you might not be needed because for standard SQL, you can just use GPT-3 like this. There won't be a need for a SQL expert, So this, I'll actually fix this after this class. It's a longer video. So look, there's so much. Okay. But it doesn't mean we all give up and just go home. SQL is still, highly valid for humans, meaning there's still very complex queries that only humans can write. So don't be worried just yet. All right, so on that note, I'm gonna go to SQL and we'll finish up this lecture and do more SQL, okay? It's all just one long lecture. Okay, so I'm gonna skip the early part and just simply get to where we were. I forgot exactly what slide we stopped, so you can remind me. But SQL is a very small language overall. A part of the language is basically dedicated to creating the tables in the first place, like create the table structure, create the indexes one at a time, view, and then you can delete them. But the more important parts of SQL are what we do with the data itself. That is what this is. So all of this is stuff that you can do with the actual data once the tables are filled. And this is where the power and the magic of SQL comes in. So we keep using this product, database example over and over just to make things pretty simple. And then if SQL was a programming language, it does not have complex data types like Python, complex number data type, or different kinds of doubles and floats and longs, that C++ has. Nothing. It just has very simple numbers, strings, dates, and booleans, just the basics that you need for starting to, put data into the system. The rest you can build, yourself. And it's like writing classes in Java or C++. You can actually write your own data type. In fact, to give you a preview, that is what spatial database is all about. You can take longitude, latitude, which are two floating point numbers, and actually make your own data type out of it. And you can call it a spatial point. That is how all of the spatial database stuff works. So these things I told you, while you create the table, you're allowed to say what is the primary key, what is the foreign key. That way it's all set up for you. And in the end, it looks like a function call. So if create table product was the name of a function, then these all look like arguments to the function. Or you can call it an object if there's a class called product, the class definition. So you're trying to create the class definition. So once you create the class definition, then you can start to insert data, and then you're instantiating objects. So then if you make a new object S1, the first row, you have to supply a value for all of these variables. And some of the values can be default, some of them have constraints. So I told you about all of that. So we can keep going. These are all good things to make sure that bad data does not enter into your table by accident. And so insert and commit. So we talked about all this. Today we'll do a little bit more about commit and rollback. But this is what it looks like. So once you have tables set up, then you start to populate the tables, and then you can put in just the columns that you want, and then the others default values are used. So these are all like function calls really in many programming languages. And then it all comes down to select, although you can update data as well. So you can select something from something and update it. So select, update, they're all pretty similar in the sense you get data from one table and you can use it to update somebody else. All right. So then the main thing about select, as you notice, is you don't write your own for loop or your if statement. But in reality, there is a for loop. After all, it goes through all the rows. And then only if this is true, that the body of the for loop, so to speak, or the body of the if statement happens. So there is an implicit if statement. Loop through all the rows and do this only for this. Hopefully there's only one of these, if this was a primary key. If this is not a primary key, by the way, like take all of the students in computer science and give them all 4.0 GPA, then that's fine. It doesn't have to be unique at all. As long as this condition is satisfied, that's going to happen. So in a sense, there's a for loop and an if statement together. That is exactly what a select statement is. So it's all about the where condition, although interestingly in the SQL grammar, where is optional, meaning, you can just do a select for no reason really. If you do select with just a few select columns, it's like the projection operation, like one of the students brought up the other day. If you want to select just some columns, then there's no where statement. You want those columns, but you want all the rows. Okay, delete is just simply delete a row of data. The whole row is gone. All right. So if there's no where condition, delete deletes the whole table. So I talked about all this. And then this is how you really put data into it, insert into, but that data can come from some other table. So then you can do a query and then grab the query and update some other table. So you can copy a whole table down onto another table, for example. The magic of SQL is subqueries, where there's queries within queries. So when, like for example, even here, when one query finishes running, then the other query can run. So this might be called a subquery because it has to completely run first and come back with some result. By the way, that result can be a single number. So if your subquery was a count subquery or a max or a min average subquery, it comes back with a single value. Then in the main query, that can be assigned to a cell value. Or the subquery can come back with a whole bunch of rows, and all those rows can be inserted in the main table. So there's some differences, okay? Or the subquery can do a bunch of rows, but also it comes back with a yes or no, like the exists subquery. So if the exists had some values, then the main query runs. Today, I'll show you a fourth variation between a main query and a subquery, where they become like a double for loop. The subquery cannot fully run at all. The subquery can only run one row of data. And then any result that it runs, the whole main query has to run all of the rows. Then the subquery can run the second row. And if that has any results, then the main query is going to run. So it is like a double for loop, a for inside a for. This thing has to run many times, okay? So that's a very interesting kind of a way to do it. That is called a correlated subquery. Okay, so where is optional? But in reality, where is not optional at all? Where is really where all the action is? And then you can use all the standard mathematical operators when you're using comparisons. So these all look like you can do date comparisons, Boolean comparisons, and definitely number comparisons, maybe even string comparisons, but mostly numerical is what we understand. This comes from standard programming, and column names can be changed so that it's simpler. And then this is operator precedence. Things like exponentiation, multiplication, division happen before addition, subtraction. Unless you have parentheses. When you have parentheses, you can have your own order, then the default precedence doesn't matter. Okay, so then that's what this was. And in reality, you start to do things like ORs. So you can combine multiple conditions, do this or that. Then your queries can become longer and more interesting, okay, like that. So this has to be true and this has to be true. Two very different things. They both have to be true. The and truth table, okay? Cool. Likewise, the or truth table. And then you can combine them. You can say this and this or that. So these all look like Boolean logic, like electronic circuit diagrams. Make a little table for the inputs and outputs. Cool. So we saw all of this, and some of these are just simply shortcuts, rather than say less than something and greater than something, meaning it's something in between. or I should have said greater than and less than, like greater than 50 and less than 100. You could say between 50, 100. It just makes it easy to write. And then this is null check, and this is string comparison. This is almost like OR operator, this or this or this or this. But the difference is when you say for something in, that in list can come from a subquery. Like find me all the vendors in, and the subquery says the vendors that I did business with last month. So that's very interesting that you can use this to hook up a subquery with the main query. And exists is interesting again because a subquery has to return some rows, and then the main query can run. So I told you all this, right? So we don't need to do it too much because we need to get to new stuff. Okay, so these are all things we've seen before. Exists is where, like I said, the main query, subquery rather, has to do something, has to come up with the result, and then that result can be used by the main query. Okay, exists and not exist. And then alter table is not something that you commonly do, but if you want to change the metadata, meaning the table characteristics, not the data, but something about the table, meaning you add a column, delete a column, or change a column's data type. It's all about columns. Then you would have to do the alter table. And many times columns are not allowed to be deleted unless they're empty. So it tries to protect you from destroying data accidentally. So if you want to modify a column characteristic, you have to copy the column to somewhere else and then empty this column out, and then change the characteristic and copy it back. So this way they're trying to protect you. That's exactly what this was, alter table. All right, so these are all, everything looks pretty simple and standard. Okay, so rollback update. Yeah, so when you want to do bulk updates, I even talked about this, you can create a brand new table and then copy from some other table in 1 or 2 steps. Although it looks like the one step seems simpler, but the one step was missing the primary key specification. So in reality, there are 2 steps no matter how you look at it. That's what this was. This looks like, 1 step, but but there might not be like a primary key. Although here there's 2 steps and there's a primary key. So in the end, there are 2 steps always after all. Okay, so alter table. And then deleting table is drop table. Cool. And then, yeah, so then this is when you're able to, do like select, this account operation. So these are all called column operations, okay? So here's where for a single column, you can say, how many rows do we have? And then the min maximum of GPS, salary, or average, things like that. So these are not standard operators that card defined because they break closure, meaning none of these are actual tables. They're not even a single table with a single row and column. So mathematically not a table at all. They're just a number, which means you can use the result from here to actually be an equal to assignment in an actual query, meaning get this number from this query and then make it be the value for some other cell in some other table. You can do that. All right, so order by, again, we talked about this. This is simply visual ordering. So if I have a bunch of prices like these, if they are sorted, it is easy for me to see what is the cheapest product, what is the most expensive product. The numbers are all scrambled, then we have to manually go look through thousands of columns. So ordering always is nice when you look at it visually. And so you can order based on like first name, last name, or in this case, last name, first name, initial. It's like Excel. You can give multiple sorts, and then it'll sort them in that order. All these things we saw. Distinct is when you don't want to see many of the same value over and over, like the same purchases name 100 times because you have 100 different products. Just give me the purchases name only 1 time. Then say select distinct, and then everything that's duplicate is counted only 1 time. All right, so like this. These 6 vendors might occur 6,000 times. So I don't need to see all the 6,000 different ways of numbering these, 6 numbers. So just give me only those 6 numbers, say distinct. All right, so these were the column operations. So they're all pretty straightforward. Think of them as just a column of numbers. So then all this makes a lot of sense. And you don't even need average because an average is simply sum divided by count, but just to make it easy, they give you average. But there's no standard deviation, or variance or anything, okay? Okay, so they're called aggregate functions. So again, pretty simple. Max, min, so max of something, min of something, and all these, so this is what I meant earlier. You can have a query whose result is fed by some other query that turns into a single number because of max. So then in this case, you're trying to find what is the most expensive product I have in my store. So you need to first of all know what is that expensive number. So you go look for the number, and then you can say, if in all my products, if anybody has that number, because you can have more than one, then give me even the description. I want to know what it's called. So then this nice little query can tell you. In our case, only 1, but if somebody else was also, the same price, then you'll see them here as well. All right, so then that's what all this was. Or you can do not just for one product, you can say, if you can combine the price and how many we have, then you can tell me what is the largest of them. So that way it multiplies how many we have by the price. And then you want to find the largest of those, meaning I have 10,000 $1 items. So that happens to be the most expensive thing that I have. Okay. And then sum is just sum. In sum, when you do a sum, you can rename the result, and then the result is going to be called total balance. So this is visual renaming, okay? Simple. Average. Yes, so very similar. So what is the average of all the items that I own? That is a nice number to have. So this is the, so on the average, if somebody comes in, that's how much they're going to spend. But then now you say, what are all the numbers above the average? That's cool, right? So who are all the students who are smarter than the average GPA? So then you do this query. First, you have to find the average, and then you find everybody that's more than the average. Then you can sort them. So then these are all by definitions, you can see they're more than 56. So all the other ones by definition would be less than 56. If you want, you can reverse it and take a look. These are all fun things that you can do to see that this all works. All right, so keep going. Grouping. Yeah, so group is very interesting because you do a group when you have aggregates. Okay, so listen very carefully. A group command would fail when there are no aggregates. This only works for aggregates. Then I think, what does that even mean? Okay, so an aggregate is an aggregate is an aggregate. But then what if it is not? What if you can subcategorize aggregations? So give me an example. Okay, so in Viterbi school, right, there are so many departments: civil engineering, computer science, material science. I can ask for a single GPA across all of those departments. So what is the Viterbi school students' GPA average? Say it is 3.5, right? Then you think, that's not telling me too much. Can you give me a per department average? That is exactly what group by. So then you would say, give me the average, but then say group by department name. Then you will get your averages. So CS average is, 3.2. Chemical engineering average 3.97. So then you go, wow, these things are different. So that is where group by is quite handy, almost like subtotals. So when you have a total, again, in your hardware store or Ralph's maybe. So Ralph's manager can say, what is the total amount of all the products we have at Ralph's right now? $200,000. Okay, that is not that useful. Can you tell me how many groceries we have? How many for milk products? How many for meat? How many for newspapers? And on, right? So then you could do group by product category. So group by is extremely interesting. And then order by is just visual ordering. Okay, so this is, therefore group by is the main thing. And then after you group, you're going to see a bunch of groups. Say for the GPA again, I'm going to see GPA all group by department. But say I don't want to see all of the GPAs even. So group by department, but then only, GPA more than 3.5. So then I'll have an even smaller number compared to this, okay? So this is almost like a select, like a where condition, but only for groups. That's what having is. So these go together. You cannot have having before you have a group in the first place. And you cannot have a group unless you have an aggregate query in the first place. So they're all like linked to each other, okay? It's pretty neat. Okay, so here's a group by example. All right. So this notion of sale price, okay, suppose you put all kinds of, suppose you put some products on sale. Some products have one number attached to them. That means they're 10% off. Other products have 2 attached to them, 20% off. Other products are not on sale at all, the full price. So then you can say, give me the lowest item price in the store. You're going to get one single number. But no, I don't really want that. I actually want the lowest price, but for all these different categories, because you're saying group by sale code. So give me the lowest priced item of all the items for which it's 10% off. So that's what it is. So give me the lowest priced item for which the sale code is 2. Give me the lowest priced item for which there's no sale code at all. The order by. If you don't do order by, usually the group by and order by would have the same value. If you don't order by, I might have 2 here, 1 here, 3 here, whatever. So then it confuses me. So I want to see them in order. So usually group by is followed by order by. Okay, this is also very cool. So now you say, what is the average of all the products that are not on sale? What is the average of all the products? 20% off, average, 10% off. It's the same thing, but again, it works because just like min, average is also an aggregate. So now I can break the aggregate down by some column. Cool. So therefore, group by is categorized, itemized. I'm just explaining. So rather than one single number, like, what is the average salary, at Microsoft? That might not mean too much, but you can say, what is the average salary per job category? On the average, how much do software developers make? What about architects? What about middle-level managers? What about, anybody, customer service reps? So that way you get different numbers, and that's probably more meaningful. Or a country can say, what about the census count, but not for the whole country, but by state. So you understand, right? Or what about, death rates for the COVID-19, but by state. So we break down things all the time, buy something, what. So that is called group by. Okay, so then this all makes a lot of sense. If you don't have an aggregate query, the whole thing would just fail. Like here, for instance, you say group by, vendor code, but there's nothing to group by. You're not asking for any kind of average, so you'll get an error. So it's not a group by expression. So as soon as you say count distinct code, so then the group by works. So this is actually very interesting. This one just says of all the different products we put on sale, then categorize them by vendor or something. It's a very interesting little query. Okay, so the main point is group by, unless you have an aggregate function, is meaningless. So after you have a group by, allowed to have having. So just the next one. So I made a store receipt. I went and shop for you guys. So then, the receipt also tells you all the different categories of things that I bought. So next time, look at your Ralph's receipt. It's actually very interesting. So then the store manager can ask, like in that category, how many products do we have? So that just tells you. So in my case, my total can be broken down by all those categories. So you can put this in a SQL table, actually ask, like, break it down by category. Should add up to our main total. In business intelligence, in warehousing, you have very similar notions. There are two SQL statements. One is called rollup and one is called cube. So rollup and cube are used for big data analysis, but it's very similar. It's all about breaking down by category, like drilling in, zooming in, and then like we're zooming out. Drill down, zoom out. So that's for another day. All right, so having once again is a where condition, but only for group by. So having filters rows in the group by, so you won't see all the group by, you will only see a subset of it because it has to meet this specific condition. For instance, in the previous version, we said, what about the averages of 10% or 20% off? Group by sale code. But you can say group by sale code, but give it to me only if the average is more than $100. So then I would get a possibly different number and maybe even an empty table because nothing satisfies that. All right, so then this is the whole thing. You need min and max before you can say group by, and you need group by before you can say having. So it's an extension. All right, so what is an example? Like here. First, you don't do having, okay? Just look at them all. So this one says, for all the different vendors that we do business with, give me the average, like how much, on the average, how much money do we spend on this vendor, like purchase. That's a cool thing to do. So count distinct P code and then average P price. But the average is grouped by vendor code. So you go to all the products and then you find out the average of all of them and then group by vendor. But now you don't want to see all of them. Maybe you're too bored. So now you say, do the exact same as before, but now having average P price of less than 10. So give me only the people that are cheapest vendors. So then you get only those numbers, right? These are filtered out. Conversely, you can do greater than 10, and then you'll get all the other numbers. So that's extremely cool that you can throw out some of the group by data by saying having. So again, only count makes it possible to have group by. Only group by makes it possible to have having. That's it. Easy, fun. Okay, table joins. Joins again are the most magical deal about all of relational databases in the first place, because join is what lets it be possible to have data in different places, each one grouped by its own role, meaning its own type. I can have student data, I can have academics, I can have sports, I can have what research, and then I can somehow take one student ID and go across all these tables and then join all those facts together. No, that's a great question, right, Ariman? No, see, conceptually, having is a lot like where, but then syntactically they're not the same. So if you go back to that query and you change having to where, you'll get a syntax error. Okay, it is like where, but it must say having. Okay, yeah, it's a great question, because where is only used for a main query. Exactly, where cannot be used with aggregates. The equivalent of where is actually having. It's a good question, but the answer is no. Cool. So joins are where everything is. Okay, so join is just simply like a Cartesian join, but then after you join, you filter the joins and you get something more useful from it. And there's a keyword called join, by the way, which I'll give you in the next lecture pretty soon, but we'll do a few joins right now. So when you join, you can also rename the columns and so on. Okay, so time for an example. This is like this. Yeah, definitely you can do both. Sure. That's a very interesting question. Yeah, so you can have a query where there's some kind of where, and then there's also having involved. Try that, okay? Okay, so then in here, it's like this. You have product, description, price, vendor, contact, area code, phone, and then now you're joining two tables. See, joining tables is as simple as listing multiple tables in the front. Okay, so because this condition that you write is going to involve one table and another table and a third and a fourth and a fifth. You can have 10 different tables and write some very complicated query. So by definition, that's a join. In this case, the join is very simple. It just simply says, tell me like the products and vendors, and then as long as these are the same. So then you simply go like row by row and you see if this is true. The product should have a vendor code for which the vendor should have the same vendor code. In that case, just simply tell me the vendor's name and the vendor's contact. So what this does is it tells you for every product, tell me who actually I should call to do a reorder. And the thing that joins them together is obviously the primary key in the vendor table is called vcode. The foreign key in the product table is also called vcode. And we assume that the vcode is the same in both tables. Therefore, by equating them, then you can put this together. This is what I mean by saying unless SQL and relational databases came along, this was pretty hard to do. Like if you had the vendors separately and these products separately, somebody had to manually go through every single product, look up a number, for example, 1, 2, 3, 4, and go through all the vendors and see who was 1, 2, 3, 4. You had to do it manually, but now you can have SQL do it, okay? So you don't need to store it all in one table. The alternative, if you don't want to do it manually, is for every product, even if the vendor's name repeat, have some vendor column and waste a lot of memory and storage and update and everything. But now you don't have to do that. SQL says, keep them separate and just tell me what you want. I'll join it for you. So that's a little join right there. But it's a lot more complex than this, but this is simplest join. Again, the bottom line is joining is as simple as listing multiple tables. So from does not need to have one table at all. It can have more than one table. And here we, just for the heck of it, for no reason, just order them a price. Okay, but you want to see all the vendors. All right, so again, if you have n tables, right, say you have 1, 2, 3 tables. In between 1, 2, 3, there's, you should probably try the connections between them, right? Say n tables, n minus 1 connections. You don't go in a loop, okay, like this. If you have 1, 2, 3, 4 tables, then you have one connection in the connection. So if you have 4 tables, you can have 3 join conditions, is what we're saying. Okay, so n tables, n minus 1 joins, all right? Then the joins can get more complex like this. In fact, just later on, figure out what this is, okay? It's like not very difficult. Amazon probably does this all the time. But I'll just point out like what is involved. There's a customer involved. Invoice means your shopping cart. See, it's place order. Are you sure? Yes. And line means every single thing in that invoice, one at a time. And product is just everything that Amazon ever ships, all the millions of things. So see what they're doing here, okay? It's pretty simple, but it's cool. You're ordering by invoice number. You probably mail them with your invoice number, and then they're trying to look for something. That's all it is. So say you have a complaint, an issue about a product, you mail the customer service rep, then they would pull the information up this way. Join it. Joins can even not involve multiple tables. You can just take one table and then join certain rows with certain other rows. That's a recursive join, and you can do it many times. Like a manager of a manager of a manager. That's a recursive join. Then you run into a small, simple syntactical problem, which is when you have 2 tables here and a table joined to itself. Then if the table was called A, then syntactically you're not allowed to say A, comma A or something, right? So you need to rename one of them. So aliases are used, okay? That's all. Otherwise the grammar doesn't look right. So like we said here, these are all employees, but employees are also managers. Other people are not managers. And so then you can take anybody and say, who is your manager? 108. And you can say, who is 108's manager? Well, that's the CEO. And so on, right? You can just go on seeing who's who or who's managers. So how would you look at a query like that? It's like this. So for every employee, list who the managers are. So basically these employees all, and you can sort it by manager. That way you'll know this manager, for example, Colmix, how many people is he and she managing. Likewise, how many people is this person managing? And you do it like this. So select E dot. You say E dot, by the way, because here's the aliasing. You say from, you cannot say emp, comma, emp or something. Say the table was actually called emp, okay? You couldn't say emp, comma, emp. You say emp E, comma, emp, M. That means temporarily call this E, temporarily call the same thing M. So now I can use different letters E and M. And then now you can do this. You can say E dot emp manager should also be emp dot emp number. So that's how you're able to do the condition, right? Because this employee's manager is that person. So as long as that is true, then list the employee number and the employee's name, and also the manager number and the manager's name. So it's a pretty cool little query. Okay, so then instantly people that work in the industry start to say, wow, joins are so horrible, joins are so slow. The answer is not that simple at all. just like with many things in the world. It depends on what type of data do you have, how many rows of data. So there's no simple pat answer, joins are horrible, joins are good. It depends, okay, you actually have to try it. So there's a long answer, there's a Quora.com. There's also like a Stack Overflow, but it's for databases, So Stack Exchange, databaseexchange.com. So they have many similar answers as well. So the short answer is, there's no yes or no. You just have to do it. Okay. So we'll just leave it at that. So don't avoid joins just because somebody says never use joins. It's there for a reason, okay? So then we're gonna stop with this very cool C# comparison. All right, so a declarative language is exactly what SQL is. It's an object, it's a set-oriented language where you simply tell something what you want. For instance, you say from P in products, when the unit price is more than 75. And then, tell me the product's name and the price. So there's a classic command, right? But in reality, what is happening is there's a loop, like I've always said. So you take the table called products, and every row, the temporary variable is called product. So for product P in products, so P is a variable. If P's price is more, there's an if statement. If P is more than 75, then tell me the name. This is what you would do in any classic language. If I gave you like a JSON file or, a comma separated value or anything, or a dictionary, you can look up of just raw data. You have to do the looping yourself. When you do it yourself, that is called imperative programming. Like C is a classic example of imperative programming. It means loops and branches. Object-oriented is then you can make a method out of it. But when you explicitly loop and branch yourself, that is called imperative. SQL is not an imperative language. That's why SQL is powerful, because we don't have to do all of this. You can do something a little bit simpler. But C#, it turns out, can support both forms of programming. If you like in C#, you can do this kind of query and you'll get the answer. Or if you like in C#, it has a SQL-like syntax. So you can do it as if it's SQL. So that's one of the few languages that does it, okay? Okay, cool. So that's it. Neat. And this last one will be just a few minutes because, at this point, already starting to do it. So I said all of it starts with an empty table, then you shove some data into it, and you start doing queries into it. This is how big data works, because you take big data, put it in like lots and lots of tables and parallel process. This is how machine learning works, because you take a lot of data with, the X values and the Y values, and then you put it in a table and you run the loop and the neural network trains itself. Then you would take some new data for which you only know the X values. You don't know the Y value. Ask the system, what is Y? It's going to output the pattern. Yeah, I have not. I definitely will add it, okay? I forgot. I definitely will add it. Yeah, thank you for reminding me. You did great. All right, so the three broad ways, again, we won't do too much of this, is you can go online, you went to Khan Academy if you like that, and just start doing your SQL coding right there. I like this one only because, someone noted SQL.js. Basically, they made a little JavaScript program that can parse basic SQL and then just run it right here. Wow, so cool, okay? So the CEO makes $25,000, right? You can actually change it, okay? So you can go here and just modify these values. So I was 75,000. Suppose I change it, really. Then your query is going to change. See that? So now CEO one at the bottom. In other words, this is live, okay? And so then if you really wonder, well, how the heck are they doing that? There's a SQL, .js. So that magic SQL.js is the one that's doing all the work. This one, SQL.js. Wow, there's a whole SQL interpreter written in JavaScript. Wonderful, right? Yeah. So then we can copy this, and then we can beautify it. So beautify.js, beautify.js. Then you will see how nicely this is written. Anyway, so there's many different ways in which you're able to learn SQL. One of the easiest being what I'm showing you. But you can do it in other ways as well. For example, you can install Oracle on your laptop, I told you. So now this is much more easily readable. See? Even then, regular expressions are pretty cool, So those are, by definition, complex to read. But otherwise, it's a whole bunch of functions. Wow, very nice. Like modern JavaScript, lots of composition chaining going on. Very wonderful. So that just creates an interpreter that runs like right here, and then you can practice that way. Okay, but that was a fun little tangent I just wanted to tell you. Try it from W3 Schools. It's wonderful, right? Because they come with this database called Northwind. This is the one that had all those customers and purchase orders and so on, right? Okay. Well, I can actually just show you the Northwind. All I wanted to show you was just a picture of what the ER diagram looks like. You can go Google it. But that data is completely available, meaning all those tables, you can just download them from many sources. And then that way you have automatically pre-populated bunch of all those tables. Then it's a seriously cool way to learn SQL. So many people use Northwind, so you can do it. The W3 schools already comes with Northwind, so you can just start, looking at it. That's really all I wanted to say. And I showed like a piece of it last time, so it's right here. See, it has shippers, orders, order details, products, customers. This should be enough for most, SQL queries, so we can learn a lot. Okay. Oh, I see. Hey, that's interesting. Yeah, exactly. Link. Yeah, Microsoft, does some very interesting things. Okay, so ID one, and again, we've gone through this. Okay, I'm going to skip it. You can create a table right there, and then, you can start to create another table, put some data into it, and then just make sure that everything looks good. And then another table, and then start to do queries, okay? You can set into like that. You can order by recipes. And then you can do it in SQL Fiddle. See, as you can see on the bottom left, it says, like a hash and then, bang 9. So that is a perma URL. So that's just a perma link. It means every time you save, you have an account with them, they'll actually save it for you. Then all you have to do is run that. That way the table is built, and you can actually run SQL. So this is all live. You can say from SQL, from recipes where ingredient equal to taco, or equal to cheese or something. So that is very neat that you can use it to again learn SQL and save all the so-called fiddles. There's Python fiddle, JavaScript fiddle, right? JS fiddle. So likewise, this SQL fiddle. Okay, so then this is the other option I told you. If you feel like you want to own everything that you touch, then you can definitely install like Oracle, Lite. This is very neat. That just Mac PC versions. That is one option. But say you want something super lightweight, SQLite, like the name says, SQLite. SQLite's a very tiny footprint relational database. In other words, if you take the same data from your homework, for example, you put it into Oracle and you measure, in terms of bytes, kilobytes, how much data, how much storage space all the tables took. If you then do the exact same thing using a separate product called SQLite, you will see that SQLite is a much more compact, a smaller footprint, a smaller file size database. Plus, in Oracle, if you have 10 tables, all the 10 tables would be in 10 different files scattered all over your file system. In SQLite, all your 10 tables, meaning your entire database, would be in one file with the extension .sqlit.sqlite. That is so cool, okay? So I'll tell you a lot more about SQLite, but then SQLite has a UI, like a front end, that is called SQLite Browser. Yeah, exactly. So SQLite, in Android phones, SQLite is actually what is holding your contact list. I have an Android phone. Actually your mileage may vary, meaning you can pick either, but personally I love SQLite. I've used it for a long time. Well, you don't need the server part of it. I mean, they both do the exact same thing for learning SQL purposes, okay? So then I'll just tell you what I was going to tell you. That SQLite browser is simply a front end, meaning you can do all of this visually, or you can type SQL. If you update this, this will update. If you update this, this will update. When you save, the whole thing will go into a .sqlite file. So for a .sqlite file, you don't need UI at all. You can have a Python command line, and you can actually do .sqlite from Python. There's a Python API. So I can run Python commands here, and actually I can loop through all of the returns that SQL gives me. Meaning in Python, my SQL command becomes a string, and then the string is sent to the SQLite engine, and SQLite returns me values. Then I can do for something in something I can write in Python. So SQLite has many programming language and APIs. In Java, JavaScript, it has got multi-language support. And the SQLite binary file format is highly documented. It means you can write your own C++ program that reads the raw byte data, and you don't even need any SQL at all. You can just simply go straight to the data and modify it. So it has many, many advantages, and obviously some pretty high-profile customers. In the meanwhile, you can download this UI. It's a nice way to get started, okay? Okay. And then there's another one. If you're on a Windows system, you can get this thing called SQLnotebook.com. It's very weirdly cool because it supports like all of SQL. In fact, this also saves to SQLite file. But in the UI level, you can write for loops, which is so weird because that is not supported by SQL. In other words, you can write imperative code, okay? So plus these all don't come with SQL. So they make it so easy to play with like all kinds of data types. So if you like, you can download, you can play with SQL Notebook as well. Very interesting, okay? But it's non-standard SQL, meaning the things that you do here might not always work in anywhere else because you can do stuff like that. These are all not SQL at all. But say you're just playing with data, who cares, right? It's a SQLite file anyway. So then there's a nice UI way to actually play with it. So that is a SQLite notebook thing that I'm showing you. And then, yeah, you can download practically anything you want. And this is just for fun. You think that there's only 3 or 4 that we keep talking about, okay? There's a massive number of relational databases that have been written over the years. Oh my God, look at this. And all the big ones that we talk about over and over, they're all right here, okay? Like wireless or PSMR. But then there's many more. See, this is the biggest of them all, right? This IBM DB2 in the Proteus. But that is like a lot. See, MySQL is popular. Because it was such a big deal before NoSQL came along, everybody wanted to do it, okay? And even now it's not a bad idea, but we get lots of nulls, so we just moved away from it. Okay, so very fast. My SQLite browser, the UI that I just now showed you, it's as simple as doing this. I made a little clip to just show you. The first thing is it asks you, where do you want to save the SQLite file? So you need to pick a directory for it. And see the file extensions, .db, .sqlite, .sqlite3, any one of them. So you have to name your file even before you do anything with it, which is a little weird. You have to name your table. This part makes sense. Anything that you type here will actually become actual SQL commands, okay? But pretty soon you can start to put some data into it. Show you. Okay, like right there, I'm just copying and pasting this. I already have from Python just a list of cosine, cos, curve goes like that. So I want to make a column of angles versus cosines of them. Something like this you can actually store in a quadcopter if you like, and actually look up like what direction the quadcopter should turn based on the cosine of the angle. So then you don't have to compute the cosine. You can look it up in a little table like that. In other words, you can do queries on it. Okay, so let's run that, and then that'll create a table, and then you can visually see all the numbers, okay? Then you can modify it if you like. You can do some queries, like show me all the angles more than 45 degrees. So here's where I'm manually putting in those numbers. Say cos 0 is 1, cos 90 is 0. Then that turns into an insert into command. Like I make the insert into commands, and this becomes visual, so you can browse for it. If you want to modify it, screw up the cosine table, you can change the values as well. Then that'll become a change command, update command. So here's the fun part you can select. This is just to show that the whole table works. But look how neat this is. This way you can learn SQL by doing some interactive UI operation and seeing what the result is, and then typing it yourself and seeing that you get the same result. So now you can do little queries like that. And that's clearly going to run cos 90 is 0. Good, right? All right, so then it's as simple as that, so please try it. When you save it, so finally when you go say save, you will get a .sqlite file. In this case, it was called first.db, but even if I made 20 tables, see, then you can see it's a binary format, but the format is documented. So this means, you wouldn't do it in Notepad. You can write Java or C++, or these days JavaScript even programs, and read your byte data. Cool. So this is neat things I want to tell you. Yeah, well, might as well. Go a little time. Okay, this one is going to show you a different example. So please look into SQLite. You'll actually like SQLite. It's small and it's well supported. And like thousands of applications actually use it because it becomes embedded, like a student was pointing out. There's no separate, database. It all becomes part of your application data. Like in an Android phone, if you actually look in the phone directories, all my contact list is actually stored as a SQLite file. If you know that, you can even make a copy for yourself and update all your contact list, just manually, meaning write code for it. All right, so this one, showing you. I'm just going to grab that, be lazy, right? Just grab it. And then you can put this into, the SQLite browser thingy, and it'll all work. So take a small number of examples like these, even though they're that simple, but try it in so many of these different systems. Try it in the JavaScript front end that I showed you a little while ago. And then you can see the differences and similarities. It's pretty interesting. So it's as simple as that. Just hit run, and then the little piece of SQL runs, and then your stuff is ready. And you can see the select command got executed, gives you nice visual results. All right, so that was fun. What I was doing after this. Just more of the same. Yeah. So then you can do more complex queries. All right. So that was my next clip. And then what else? Yeah, so let's look at this SQLite. All right, so SQLite format. If you wonder, wow, what was the whole binary all about? How do I read it? All right, so if you go to SQLite.org, file format.html is all you have to know. If you like writing low-level code, actually byte processing code, then this is for you. Other people have done it, by the way. There's all kinds of SQLite parsers, but you can write your own if you want in any programming language that reads bytes. So there's actually pure binary data. This way, somebody that uses this in an application would not have to worry that SQLite is going to be not supported in the future, because we know the file format, so we can always get the data. Data is never going to be lost. It's forever. It's right here. So that's neat, okay? But most people don't care about this. It's in there. And yeah, SQLite calls of so many languages. So I talked about Python, right? This is what you can do in the Python shell right here. You can say for row in C.execute, there's a string, Python string, but that's SQL. So say I have stock data, then I can say select star from stocks, order by price. Then that will be returned as iterable, meaning like an array of strings. That is why I have for loop here, and I'm just printing it. Then Python prints it. Unicode, that's you. But it's so neat that I can mix Python. In other words, think about how else you might do it, right? So SQL does not give you a good way to format data, what, right? So then this way I can get from SQL what is good for, and then I can do anything afterwards myself. I can even put it in a NoSQL database. So it's a nice way to go from relational databases to like JSON right here. You can do like lots of neat things. And like I said, you could write your own parser, but it already exists. You will never lose your data. And so who is using SQLite? SQLite sounds like a pretty cool little thing, right? Adobe uses it, probably for their Photoshop products, right? Lightroom, that's neat. Airbus, Apple, Bentley. I mean, these are top companies in the world. $2 trillion company. So if they can use SQLite, then it's good enough for you, right? Facebook. So they have good company. So look at SQLite. Yeah, everybody uses it. I've used SQLite in the past at DreamWorks. You can store animation data this way. Right. Cool. And then cloud-based. So finally, after all, if all this is not enough, and you can still forget all that, I can just have a free, AWS account. And then they have the relational database service. They call it RDS. It comes with many different relational databases. They have Oracle. They have their own. They have, different kinds. For example, Maria, SQL Server. So you can program in any of them. They're all pretty similar. But with spatial databases, they have a slight different syntax for their libraries. So depending on which one you like, you can run them. But otherwise, they all do the same thing overall. And yeah, then the free tier, comes with 5 gigabytes or something, should be enough for most purposes. But if you want to store more data, you want to do more calculation, you can start paying them for it. Yeah, so then the whole cloud stuff entirely exists, okay? And look at, again, all the crazy cool people that are using it. Your usernames are probably for USC up here in AWS somewhere. All right, so that is the third way of learning all this, okay? So Amazon gives you stuff, and likewise, GCP, Google has very similar things. Azure also has very similar things. So 3 broad different ways. One is entirely in your browser, nothing to install. Second is you can install small programs, big programs on your machine. Or third, you can just go on the cloud through your browser again. But it's not running on your browser, it's running elsewhere. Hey, cool. Okay, that should be enough. That was our last slide from the standard SQL, right? But more SQL. So the book calls it like advanced SQL, but it's nothing advanced about it, right? Just simply more SQL. So what are some other things that we left out in your core SQL coverage? They just call it advanced. So I'm going to give you a rundown, okay? And it's very easy again. Just in other words, more things that the language actually lets you do. In this part, you can actually see that SQL resembles a little bit of a programming language. Like you can write functions in SQL. So far, we never talked about how do you write your own function, or how do you write your own class. I hinted at that. You can make your own data type. So now I can tell you a tiny bit more about all that. So join, there's an actual join command that you can do without naming multiple tables and using like where conditions. That is one way to manually do any join you want. But there are actually words like inner join, outer join. So then they make it a little bit easier to join. All right. And then this notion of a correlated subquery, this whole double for loop thing. So for some reason, queries become connected like that. So that's a good thing to know. And then also, these are just standard SQL functions. I'm hardly going to talk about this. Like with any programming language, SQL has built-in functions for things like manipulating dates. Okay. Like you can convert, for example, from a US format to European format, or you can take a string and capitalize just the first letter, or maybe capitalize all the letters, or remove underscores. Classic string processing functions that you find in C++, in JavaScript, in Python, whatever. It's the same thing, in SQL. So you can just look all this up, and they tend to be slightly different for each implementation. So you almost have to just go back and read it. And then I can tell you about union, intersection, and difference. Difference sometimes is called minus, but otherwise it's called difference. Set operations. So nothing new at all. We talked about all this, but just examples for them. And then finish up with function calls, functions, and what's called procedures. A function returns something. A procedure does not return something. Old-fashioned Fortran, Pascal difference in those languages. There's a difference between function and procedure. So then SQL also has the notion of a function and a procedure. In a procedure, you run a bunch of code, it updates some tables, and you're done. In a function, you do a bunch of stuff, and it returns you a value, which you can use to populate some other table if you want. Okay, so that is the very end of what we do here. Joining is pretty simple. It's always, by definition, 2 tables, although recursive join can be in 1 table as well. So I'm just reminding you of the join that we saw. So one way to join is literally name tables in the from part, and then in the where part, connect them somehow so that you have to jump from table to table. Then you can do some pretty complex operation. Like whatever you want is technically called the join. But then, what if you want to do simple joins and not even do all of this? Just say the word join and just do it. Those are called join conditions, okay? Okay, so the simplest join conditions are where we manually do it ourselves. Again, this is a lot like the previous slide where you're writing a join condition. But here's another example. Okay, so first of all, joins most of the time are done with equality. You say something equal to something, so by definition, you think that those two are glued together. But amazingly, joins can also work on the 5 non-equal to equal to operators. They can literally not equal to, greater than, less than, greater than or equal to, less than or equal to. Those conditions between any two cells can also be used to join those 2 rows together. In other words, join 2 rows if the salaries are not the same. Just think about that, okay? So cool. Or join 2 rows if for some column, in one row the value is smaller than the value in a different row in a different table. Join them. Wow, that is possible. Those are called theta joins. So a theta join is all the inequality joins. The equality join is called an equijoin. So equijoin versus theta join. Okay, so in this case, just simply, who are all the students will get an A, okay? So then you can do this. I got it from that site. So then select, somebody's name and then somebody's score. So I have a list of all of the scores, and then I have the grade range. Like after this course is done, that's what I'm going to make a little table that says 95 and above is an A, 90 to 95 A minus. So suppose that's what this is, okay? Then that's what this says here. So this says, for somebody, the grade needs to, like in the grade table, the grade is A. And then for the student A, the score is between low and high. So this is a whole bunch of rows. So B has a whole bunch of rows that says what is A, what is B, what is C. So then for A, there's a certain range that I know from this B table. So who are all the A students who have that range? In other words, if I know that A is between 95 and 100, then tell me all the students who fall between 95 and 100. It's pretty neat. And then for the students, tell me the score so I can look at it between 95 and 100. But more importantly, give me their names, okay? So that's a cool condition. But that is not the join command because we didn't say the word join. So there are actual join commands, which we'll look at next. By the way, you can do this yourself. So please make 2 little tables like that and then put a bunch of people's names, put your own name in, and then be in the A range and run this and see if your name shows up. Okay, it's a fun little command. Here, by the way, you can say between, okay? You can say between something, comma something, or you can say, A score more than B end, and also A score less than B end. You can always do it like that. Okay, join operators. Join is so important and popular that over time, the SQL standard has been revised many times. The SQL committee gets together and says, what else keywords can we add to the language? So that is why there are these old style, new style. So don't be confused by all of it. It's all the same idea. But there are so many ways to do exactly the same join. And the same join is just simply this. I have 2 different tables. Okay, the tables might be called athletic tables, academics table. But the 2 columns, like 1 column in each table, or the same name. The column has the word student ID. So in the student academics table, there's the word student ID. And the implication is that is every student ID. In the sports table, as a foreign key, also the same column exists. It's called student ID, the same name. Then we make the logical assumption. It's probably talking about the student. The student ID does not mean something else, sports ID. So as long as you know that, how do you then combine those 2 columns? In other words, for every student, I want the academic information and also I want all the sports information. That is exactly what join is. Okay, so first of all, cross join. When you say select something from 2 tables, that's all you say. This is doing a Cartesian product. It's doing a multiplication, which I showed you previously, where the total number of rows in the result is number of rows in T1 times number of rows in T2, because every row is joined with every other row. A number of columns in the result is what? The number of columns in this would be, number of rows would be rows T1 times rows T2. Columns is what? Columns is, yeah, plus, exactly. So the number of rows in T1 plus the, number of columns in T1 plus the number of columns in T2. So it's just a product, okay? Okay, so this is useless in the sense you're going to get fake data, but it's a partial step before you go and filter it. For that, you can do it this way, or you can actually officially use the word cross join. So this way it makes it pretty obvious if somebody reads it, oh, they're just multiplying the tables together. And then you can take the result called a view, and then you can do further operations on it. So forget that, that is actually not joining data for any useful purpose. So the actual join starts from this column. It says inner join, which is classic join with only the rows that match, no other extraneous, like empty values anywhere. In the old days, you would say it like this. You would say select star, give me all the column names from both tables, where, again, join condition. This is exactly like this or exactly like that. So we keep going back to that because, that's the most powerful way to do it. But we called it the old join style. So then the SQL committee said, we should call it natural join. Like we don't even need to, specifically say that this C1's in both. Let the system find it itself. So when we say select star from T1, natural join T2, natural join means every column name here would be compared with every column name in here. So as soon as a column name is found to be common, then that column is going to be used for joining, which is basically just exactly this. But now you can just say the word natural, okay? Like this. Same names, and it's not just the name should match, also the type should match. You cannot make one into a Boolean and one into a number. Then obviously it cannot work, right? So it's just logical. Okay, so a different way to say natural join is just simply, say using. You can say join using. So from T1 join T2, join them together. Or you can say from T2 join T1, using that column. So it's pretty much similar, but now you say using. But here the difference is if somebody reads it, if somebody reads this, they don't know exactly what column is being used. It's almost like a hidden thing, right? But now it's not hidden anymore. It's as open as this one, but it's not an expression. It's the word using. So they're all like doing the same thing in different ways, okay? Or you can do it like this. You can say join on. So from T1 join T2 on the condition. Now the condition is back. Oh my God. They're taking this condition and then putting the word on it. Or they're taking the column name and then saying using. Or they're throwing it all out and just saying natural. Right? Look at this. Wow. Okay, so then, doing the same thing in like multiple different ways. Just think about it. Okay, so now the whole left, right, and full. I showed you a little clip last time, so you know what this means. So in the left join, regardless of what joins happen or not, every single row from the left is going to show up. Returns all the rows matching values in the left table, even unmatched values. So if there's some row on the left-hand table for which there's no match on the right-hand table at all, you're still going to get it. Very good. I was hoping that somebody would ask it. On purposely, I said every column in T1 is going to be matched with every column in T2. So the most obvious question to ask is, what is this more than one? Then they'll all be used to match. In other words, match will only happen when, say there's column A and column B, right? Here also there's column A and column B. Then there has to be a row here and a row here where A matches A and B matches B. Yeah, in natural join, which is why if that happens, suppose there's multiple columns all over the place, then if you want to be sure that you're only using C1, then do it like this or do it like this or do it like this. Makes sense? Then C2 will not be used. Cool. So here's where the question happens. When you have like multiple columns matching, then the answer is all of them would have to be taken into account. Because it does make sense, right? Because why would you leave what is the criterion for leaving something out? They're all equally valid, and so they'll all be used. So if you then still want to use only one of them, then you have to name one of them either here or here or here. Okay, cool. So try it as well, okay? Just for fun, do that. You'll see that works. But that was a good question. I was waiting for it. I was actually a little sad. No one asked me. Then Hamza said, what about that? All right, so left outer join, select star, again, T1. Now you say left outer join T2. By the way, in all of this, there's an implicit left-hand side and a right-hand side. So regardless of what the words are, T1 is on the left, T2 is on the right. If you want to swap them, you want to see all columns of T2, even with the left outer join, then you swap T2, put T1 over here. So left means in this whole syntax, something on the left-hand side. Okay, so in this case, this means, look, use this as a condition, but tell me all rows of T1. Same thing, but tell me all rows of T2. This means tell me rows of T1 and T2, regardless of blanks on both sides. Again, please go to the little clip that I put up last time that Yash sent me. Cool. Okay, so then that's all there was to it. And you can look at a tiny example here. It says select all these things, what from vendor full join product on vendor code. So this is just a full join both left and right. So you see, for all these products, we got vendors, okay? But because we said full join, there are going to be products. Sorry, there are going to be products here for which we have no vendors. If you want to reorder these products, you're out of luck So you don't know who made it. Conversely, these vendors are not even doing business with us because we absolutely have no products from them in our store. Probably should delete them from our contact list, right? So that tells you these nice things, these holes are being exposed when you say full join. If you don't say full join, you'll only get this top part. This will be all cut off. You can even try that, okay? So full join is only matches. So sorry, actual pure join, natural join is only matches. But when you say right, or when you say left or right or full, you're gonna see like holes as well. Is there any difference? No, not at all, because in the end, they all get compiled by the SQL engine to exactly the same kind of access. That's a SQL compiler, by the way, okay? It's exactly like a C++ optimizing compiler with even -02. It is pretty aggressive. It can do some very amazing optimizations. That's for another time, performance tuning, where almost any mistake that you might make or any inefficient way that you write or multiple ways you write stuff, they all end up being compiled to pretty much the same access. You can even, by the way, find it yourself because you can do the same query like 3 different ways. And then we're actually allowed to look at what the compiled result is. That is called an access plan, by the way. So an access plan is pretty much compiled SQL. And it looks amazing because it looks nothing like SQL at all. It has raw, table names and like the hardware storage, and it has row IDs and column IDs. Just literally telling you how it's going to fetch the data. And then you will see that they'll all have the same access plan, hopefully, where you can check it. Cool. Okay, so select subqueries. Behind. Okay, it's okay. So select subquery is this, not because of ESRAG, by the way. Okay, please keep asking me questions. Okay, so the questions are not the problem at all. I'm just behind. Okay, so subquery is just a very simple idea. We've seen subqueries before. It's not a new concept. A subquery is just the idea that the main query has something else that is holding it up. Only when this runs, the main query can run. This makes a lot of sense. See, here we're literally copying everything from P to product, assuming product already exists. We saw an example of this. So make an empty product and literally select all rows and all columns and just show it in the product. Then you can delete P if you want. So now you have a copy of P called product. Or you can do very similar things. Maybe you want to do that, but now you want to be selective. Maybe you bought somebody's hardware store. And so this is the other person's hardware store. This is your hardware store. Maybe you don't want all the products, Maybe you want to, just only have, or maybe you're trying to find something else. So in your store, you're trying to set this cool little thing where you're trying to set the price where you find the average price. But for this condition, so the vendor for this average that you're doing should be this vendor. So only look for 615 area code vendors and then take all the products that they sell and then find the average of that and then set the price to be equal to that. It's like a weird little query, by the way. That's what this says. So set the product price to average price, but only for these products. Okay, set that price. So all the products supplied by this vendor would become that single average price. That is so weird. This one, if you're not doing business with this vendor anymore, delete. So again, before the delete can happen, you need to know whom to delete. This is what I meant earlier, okay? So sometimes select queries can become like a list, like an or, this or this or this. Therefore, you come back with the vendors, and then as long as any vendor matches in your product, that product is gone. So you're not doing business with, you don't like area code 615. Okay, so don't do business with them anymore. Boycott them. The whole area code. That's what that is. Okay, so now we come to the correlated query part. Okay, this is the main thing. Okay, and please listen to this. I told you this. When you have a single value that is coming from like a max or something, you can use it to assign to a cell. When you have a list of values like here, you can use it for the in condition, or you can even get a whole table and you can do something else with the table. When you get a table, you call it a virtual table. It's like a table in memory. Or if your conditions are totally screwed up, then you'll get nothing. So all these are possible. But what about correlation? Oh yeah, where? Yes, so let's talk more about where. Okay, so we've seen so many wheres. Okay, there's nothing new, but I'll tell you more about wheres. So this means like this, a where subquery. I'll magnify it. Okay, so look at this. Again, select these things, go back to the product. So select this product, select the price, where, good old where, from is already here. You run this. So where the price should be more than that. So this again is a number, right? This becomes a number. And so then I can use this where condition over and over and over in my main store. And then I can tell you all the things in my store that are more than the average, right? Because that's all this is. Okay, so we were saying that before. And then you can do this again. If you want to find out like who bought the product, Then you're able to do a similar, where subquery, where you can just select like all of these, select the customer's name, what. But then do this join. So do the join because the invoice is what tells you who purchased what. Then the invoice contains line numbers. Line numbers, contain products. But now look at the product and see if the product is this product. For the claw hammer, look up the product's product code and see what customers ordered it and tell me who those customers are. Supposing that product started to kill people, right? So, somebody's hammering like a nail into a wall and then the hammer head flies off and kills a baby. And the hardware stores to go, oh my God, I got to recall like all these claw hammers. So who else did we sell it to? So we need to call those people and have them bring it back. Our car has, for example, a problem with the airbags, okay? The airbags deploy prematurely, accidents happen. Then Toyota says, well, we have to, recall like 1 million cars. This is exactly what happens. And find out who are all the people that have that feature installed. Then, give them emergency calls. Bring your vehicle in now. So then, that kind of a query actually helps you. But we call them where subqueries because subquery happens in the where part, which is the most common place where subqueries happen. But amazingly, subqueries can happen in other places as well. Okay. So in subquery, so this is what I already went through, right? The in example. So tell me all the vendors who are in 615, and then let's delete them. They're called in subqueries. We just give a name to all these different subqueries. So the having, you already saw this again, what one of the students was asking, so having is having, meaning when you have a group by, then the where condition is called having subquery. So we're just naming things we've seen before. So there's nothing new here. Again, we saw an example just one more time. Like here, this is a slightly different example. So here, this one says, do all of this, but then now, not just a claw hammer, we want to get all hammers. So therefore you can say like something, but then again, the description will come back to in. So like this query, you match, of all the things that people bought, what are all the things that have the word hammer in them, and then find out who bought them. So this way, any kind of hammer, ball hammer, peen hammer, all kinds of hammers, claw hammer, pick them all up. But it's called an in subquery because in the end there's an in here. Okay, again, we've seen all this before. Having subqueries, once again, you've seen this before. So then here you can say group by, this line unit stuff. But then you say having some more than. So do a group by, but don't show me all of them. The group by only show me as long as this condition is true. So find the average. Then find, all the people that ordered more than the average. So on any given day, right, I could order just one thing, or somebody could order 20 items, say from Amazon Prime. Then this one says, tell me all the people or tell me all the products for which more than the average was ordered. That's all it is, okay? So there's an average, but then now, you want the order to be more than the average. So what are they? That's all. For the previous example, could you use P equal to? Good question. Equal to only matches one value. In actually matches like a whole list of them. So the short answer is no. These are the tiny things that SQL maybe trips you up in the sense you try it once and it doesn't work. But then you quickly realize equal to is strictly an equality, okay? Equal to is basically like an assignment. And so then the right side of equal to has to be a single value. But in is more like, or this, or this, or this. So we cannot use equal to. Make sense? Cool. All right, so that was having. And then there's also all any. So these are like, ands and ors again. So what are these? So these are called multi-row subquery operators. So the in operator is again, either this or this or this. It's an in comparison. Say you have a Python list, then you're saying, oh, you're this, or you're this, or you're this. Go through all the list elements. So likewise, you can do an inequality comparison. Suppose you have a list of prices. Okay, you have a list of prices. And then suppose you want a single price in your product. There should be more than all of these. So say I give you 10 different dollar amounts. Then I tell me all the things in my store that are more than all of them. So that means you're actually saying it doesn't matter all of them. Just give me the largest of these. So then I'll give you something that's even larger than that one. So then, in other words, globally greater than all, greater than all. So likewise, I can do need to be less than any of them. So I can give you a bunch of numbers. And then I can ask you, tell me all the things that are less than any of them. Then what I would do is obviously find the smallest value and then find things that are even smaller. So for those, we use all and any keywords, okay? That's all it is. So all operator allows the comparison of a single value, like say the price of things in your store, with a list of values. So your initial query, subquery is gonna come back with a list. And then all says, I'll take the list and give you something that's bigger than all of them. So likewise for any. Again, my subquery comes back with like a value, and then any compares with your existing values and says I'll output, matching any of them. Say any versus all, okay? So again, an example makes it very clear. So what products do we own in our store whose value is more than all the other supplied by vendors? So again, you go to Florida, like Florida a lot. And then we say, take all the things that the vendors are supplying, but as long as they're in Florida. And then take all the prices of all the products that come from Florida. But now in my store, tell me all the products whose value is more than basically any of those value, all of those. Yeah, even though it's all is actually any, which is the highest number. So how do you do that? This happens to be a product. It's like this. So not the product, actually the value, total value, meaning product price times quantity, basically product. Managers might loosely say, how much product do I own? What actually mean is not just the price, they actually mean quantity times price. Is what we call product. But this is the cool part. That thing that you're comparing and outputting should be more than all of these. All those combined, what you call product, but only for these vendors. So go through my whole store and do this multiplication, but only for those vendors. And that becomes a list. Then go to my store one more time and do the product calculation one more time. It's a waste of processing, right? You got to do it for the subquery and you got to do it for the main query, row by row by row. But now you try to see if your main query is more than any of those subquery in values, meaning more than all of them in the list. You'll get the globally max value. So greater than all means greater than the greatest of. That's what I told you. Cool. So likewise, any is the complement of that. It's like this. Again, select rows, because you can have more than one row that satisfies. The comparison succeeds with any value in the list. So my list can have 3 items. If my price value matches any of the 3 items, I'll put it. So it's like an OR condition. My price matches A or B or C. You can literally say any of A, B, C. All right. So therefore, any is like an in operator. Somebody should ask me that. And in is like multiple equality comparisons, with ORs, right? So they're all the same. One way to do it is to suppose I know the values, then I can hard code in SQL 6 or 8 or 10. If I don't know the values, I can do a subquery, make it come back with a list and say in. And then to answer your question with the equal to sign, you can do this, okay? Then you're doing comparison. Yeah. So the student asked a very smart question privately. When you have a list like this, can you do an equal to? With the in operator. So the in operator, you cannot do an equal to. You must only say in, but you can do an equal to with any operator. Hey, private student, does that answer your question even better? I want out you. Yes. The person said yes. Okay. So, moving on from subqueries. Yeah. Okay, so now is when it starts to get more interesting. I'll draw a little diagram for you. SQL can produce a cascade of SQL operators. There are 3 ways to end. What does that even mean? This. Select something from something, where something. So far what we saw was in where you can have a subquery that says select something from something, where something. But now I'm going to tell you select something from something. The from can be a table, what. But another select something from something, where something. I can stick a query here, which after it finishes running will become a table, and the table can be used for the main query. Wow. This means we can keep going. So in here, I can now again select something from something. I can go in the from and actually have a little subquery. Select something from something, where something. Or for that matter, I can do it here as well, because it's a where, remember? Where, select something from something, where something. And here I can do it too. Select something from something. I can make a little thing there, and then I can make a little thing there. OMG. For the from table, would you only query table names? Right. Yeah. So this can be a combination of table names and also what are called virtual tables, which you can name, by the way. You can name something. So you can take the whole query and name it something. Then it becomes as if you had a table in the first place. That name can be used in the query here. Yes. Okay. So then we're not done. In this here, in the select part, you can also have select something from something, where something. Wow. This is a cascade, right? So that can give you this kind of a shower. And then each one of those can again give you potentially, nobody writes SQL like this. It's crazy. It's madness, right? But if you want, you could write the most complicated SQL where every single part, the select part, the from part, and the where part can have 3 pieces, right? It's SQL. But you can keep on cascading like this, like the most complicated query ever. So after 6 months, you have no idea what the hell you did there. So you need to be careful. But if you have complex, conditions, then SQL gives you the power to actually do that. So right now we're looking at what are called from subqueries, okay? Where the word from no longer just says table names, but then it also has the results of SQL queries, which are called virtual tables. That's funny. CJ, you should try it. Just purely because you can. All right, so then what does it look like? There's a from that you already know, but now you have a select where the from appears, and you can name it. The return type is subqueries. Yeah, definitely, exactly. So, some of these don't work. That's a great question. Dorima is asking. In the from part, you cannot stick a subquery that returns a number, because a table cannot be a number ever, okay? A table can be a single row, single column number. It has to have closure. So the max operations, etc., cannot go in the from clause. It's a great question. Yes. So it's not completely free for all. It has to make sense. All right, so where's like one of those? It's right here. All customers who bought both specified products. Okay, so now you have two products. Who are the ones that both bought like all of them, right? Give me their customer ID. So select customer ID, customer's last name from customer. Okay, so from customer, comma, that's an actual table, customer table. But this here, select invoice, like all of this, what, right? That is actually not a table, meaning that is coming from the select subquery here. So that, in fact, that select subquery, you call it CP1. So it's customer, comma, CP1. CP1 is a virtual table. Another query, comma, CP2. So the main query where you have this customer code is matching CP1, CP2 is coming from three tables. Of the three tables, only one table is real. The customer table is real, so it's customer code. This CP1 can only happen in memory after this subquery finishes executing, but then that CP1 can be used in a result. How cool is that? Likewise, CP2 just pops you into memory only when this select subquery finishes running. Then CP2 becomes real in memory, and you can run these, and you get a result. In other words, you can create tables on the fly when the main query is executing and call them something and use them in main queries where condition. Wow, right? It's amazing. If you like, you can do what is called persist. You can do what's called a material view. A view is just simply, these virtual tables. But you can write CP1 to an actual table. You can call it CP1 or even call it something else, like, customer process one. Then after that, you don't have to do this at all. Then you can say from customer, comma, customer process one, comma, customer process two. Meaning you can save all these to memory if you keep doing the same thing over and over again. But that's possible. But right now, we'll just say that it's a virtual table. But it's so cool that you can name them. Otherwise, how would you refer to the table, right? It's more like an anonymous object. So you have to name that object something, and then you can use it in a query. So please go through this and see that you understand this, okay? But it's neat. The subqueries that occur at the from level. So these are called from subqueries. Likewise, the last part that I drew up on the top, where they select the column name, those are called column subqueries, or they're called attribute list subqueries, because columns are attributes. So these subqueries determine what columns get output by the main query. They can be actual columns or computed columns. So columns can also come from SQL, okay? Or, meaning you can do straightforward computation, or you can even do max functions. But at this point, it's not really a table. So I want to show you. They're called column subqueries or inline subqueries. They call them many things, but they all do the same thing. They're pretty much writing SQL at the top, meaning at the select part of it. All right. So then if you do that, then that column that is being created cannot immediately be used in the where query, okay? Because, they're all running as part of the same process. So if you do that, the column, unlike the from part of it, the from condition, the from subquery became a table, then you can use that in the where condition. But then now if you do it at the very top, at the select level, then you have to accept what the table gives you. It cannot be used in its own where condition. Okay, so what does it all look like? It looks like this. Select product code, product price. Look at this. Select average price from product as average price. So this column you're creating as a result of SQL command that appears at the select level. How cool is that, right? Again, real column, price real column, calculated column that comes from a SQL command. And you just leave it at that. Like you don't use average price over here in the where condition. Yeah. Because they're all running as part of the same operation. In other words, when you get to where, this is not ready yet. Look at catch 22. Okay, so select average price from product. You're just basically making a whole column for average, which is actually wasteful. In production, you would probably hide it, right? But you can do something more cool with it. So after you make average price, that column called average price, You can say, tell me all the products. So now it's up or down, okay, plus or minus. Every product then, except unless you're exactly the average, it's either above average or below average. So then you simply subtract the average from the product, like here, like CP is P price minus average. So if your P price was higher than average, you'll have a positive number. The P price is lower than average, you're going to get a negative number. If the P price was exactly the average, just this value, then you'll get 0. That's pretty unlikely. So then everything becomes a plus or a minus, right? You call it up or down. That's neat that you can do that. In there, you can definitely use average price because for every row, this operation happens. So then you can make a new column. You call it difference. In the end, this is really what you want. You want to know who's more than average, who's less than average. But in the meanwhile, just for checking purposes, you can even print average price. But if you give it to somebody, you'll probably remove that line that says select average price from product average price because it's wastefully telling you the same number over and over again. Makes sense, right? That is called the attribute subquery. So one more example, okay? Just so that you can really understand. So this one selects product code, so far so good. So sum of line units times line prices sales. So this, how many things that customers bought. So line units means how many items and what is the price of each item. This is how much sales we made. And then select count star from employees. So this is actually very interesting, okay? You're trying to reward employees who actually sold those products. That's actually what is happening. Because you're also doing this e-count. This e-count is coming from select count star from employee. So for all those employees that basically service those, employee count, but there's only one employee count, right? The same employee count over and over again. But now this last column is very interesting. So this one says sum line units times line price. We already saw that, but divide by the employee count. So this means on the average, for all those products, how much did each employee contribute, so to speak? It's like a weird thing, right? Like divide this by this, divide this by this. Then you can get that. So for that, again, the point here is just to say that for the column names, only the first column name is real. Second column name is computed. Third column name is also computed. Fourth column name is also computed. They're all computed columns. That's really all. And then for no reason, you're grouping into a product code. Like a weird thing. How much did each of the 17 employees contribute to the sales of each product? It's like so bizarre, right? Yeah. Maybe there's some need for that. Like fake example. All right, so correlated subqueries. Now we come to the pretty important one, although important but very simple. SQL-wise, syntax-wise, there's no special flag that says this is a correlated subquery. The SQL engine is not alerted this is subquery correlated. It's correlated just because of the column names. The way the query is written makes it impossible for the subquery to run as this one operation and come back with a virtual table that the main query can use. I'll pretty soon show an example. It'll make it pretty obvious. Instead, what will happen is the subquery runs one time, and the main query would then use that one value the subquery returned and run itself one time. So it's a loop within a loop, okay? Like an image processing operation. I'll actually draw that so the correlated subquery makes a lot of sense, like this. Suppose I have this graph paper right here, this little thing I'm looking at. So then for every row, you have to go through every single column. This way you visit pixels in an image. So for that row, go through all of the columns, then go to the next row, go to all of the columns, then next row, go to all of them. So then you would do loops, right? You would say, for example, for I in something like, in this case, XRES. So say XRES is X resolution, like X resolution. But then inside you'll have a for J in Y resolution. You have for J in Y resolution. So Y resolution tells you, how many columns you have. Then you would do I, J, access the pixel value, brighten it by 10%, stuff like that, right? But that's a double for loop where J has to run for every single I. So if I is 0, then J has to run through this. The next I will become 1, and then J has to run. So the inner loop has to keep on running many times, once for every outer loop, right? That's pretty much it. So let me show that to you. It's a very neat query, correlated subquery. Okay, so the inner subquery is repeatedly run. So the inner query cannot just finish. It has to run every single time. So basically what's happened is the outer query gives you like a single row. Outer query has lots of rows, right? So your table has lots of rows. So then, in other words, it's all the employees that are in your company. So for the first employee, take the salary, whatever the salary is. That salary should be more than this right here. But now what you're doing is you're saying select the average salary. So look at what's happening from employees, right? But the department should be Bob's department, okay? So you're doing like all of this. So you're taking this table and for some crazy reason, calling the employees table as Bob, okay? Just rename the employees table. Then there's a Bob department. So every row would have its own department. So then you take that salary, and then you go here, and then you say go department by department, and select the average salary, but only for the department. So say the first department was, I don't know, R&D. Then this one says, go through and then find the average for salary, but only for the R&D department. And then in the main query, come back and say, take all the people who are making more than the average salary for the R&D department. Then the second row would take whatever the second row employee is, say marketing, and give the marketing to the subquery. And the subquery goes and runs many times and comes back and says, if anybody who is part of marketing, then find the average salary. And then the main query is, okay, I'll take that and then pick out all the people that make more than the average in marketing. Like, wow. So the main row is feeding one row of data at a time to the subquery. Subquery keeps on running over and over. Returns back result to the main query. The main query can run yes or no. So row by row, the main query is running. But every time the main query runs, the subquery has to completely run fully for the whole table. Wow. Weirdly, interestingly odd. That's what this is. So the inner query is correlated because it's referring to some column that needs to match. Whoa. It's a double nested for loop. So if you like to read a little bit more, not commonly used in practice at all, okay? Because there are other ways to write the same thing, but you can read it. Okay, that is correlated. But there's nothing special about the syntax. You're not marking anything. It looks like any average query, but the department name, okay? That's very interesting. So this means implicitly the main column is passing like a department. And then you have to match, what you call Bob. Cool. So the outer query passes in for each employee of the main row, the employee's department. Then the inner query calls that Bob the department and runs one more time. So the inner query, every row is still called department, but you're matching with the one value that came in from the outer query. This is a single outer value, I equal to, the top row of pixels. Then this is all the columns in the top row of pixels. Then I go to the next row of pixels. This is the second row of pixels. I go through all the columns. Then I get my third row of pixels. I go through all the columns and so on. So I go row by row by row in the image. That's what Bob department is. And then I do this looping over and over. So for each row, I visit all of the pixels, so to speak, in the image analogy. So I'm stepping by rows and columns. So I'm doing a double for loop. Yeah, interesting. Okay, so you can look at this. You can even run this, by the way, and actually see it works. Okay, so then the analogy that I just made is like over here. Say x runs from 1 to 2 is 1, 2 is 1, 2, 3. So when you print them, obviously, x is going to be stuck at 1, and then y has to be 1, 2, 3. Then x is going to be 2, then y has to be 1, 2, 3 again. That's all it is. So the outer query passes like a row of data to the inner query. The inner query has to run through the whole table with a single piece of data passed in, and then sends something back to the outer query. The outer query is still on the top row, remember, and it does something with it. Then the outer row steps to the second row, outer query, and sends some data to the inner query, runs over and over and over, sends result back. Then the main query takes that result for the second row and does something with it. And then the main query takes the third row of data and sends it back to the inner query, runs over and over and over many times, send back result. So you go here, you go there, you go wherever. So it's cool, right? You're just simply playing with data. You got results from somewhere, and you have to loop, and then you have to go back. Neat. Okay, so, just more examples like that, okay? Again, the outer query is sending me something, and then I have to use it in the inner query. I call it ls, and then I'm going to do my own thing because in the inner query, I'm calling myself LA. So every row of LA would have to be matched with one row of ls that came in and give you something back. Then I give you one more ls, and then I have to use that ls with my own LA run. So this is like the outer loop variable, inner loop variable. Yeah, exactly. It is like a nested for loop. That's actually what I said. Sorry. I said it too fast or something, but yeah, this is a nested for loop, right? See, in image processing, this is quite common, so I just take it for granted. When you want to blur every single, or say you want to brighten every single image, that's exactly what you do, because your image is a two-dimensional grid, and so this is the pixel coordinates. This might be the row coordinate, this might be the column coordinate, then comma is the pixel value. So yes, for every time the outer for happens, the inner for has to completely finish running. And then outer for changes the variable one more time. In other words, give one row of data to the inner query. The inner query has to run through all the rows of data with the one row of data that you gave me, and then send some result back. Then the one row is processed. Then the next row, x equal to 2. The inner query is given some data. The inner query has to run through all the rows again with that one piece of data that came in, send result back. So it is a double for loop, yes. Cool. So in this case, one more time, this is like the outer query, meaning this is like the row of when I have the image processing, first row, second row, third row, fourth row. So each row we call ls. but that's only one value at a time. But for the one value, this has to run. It means it's the inner loop and send some result. And then that first row, for the ls row, you can do some decision. Should I output that or not? Then you're outputting values, okay? So these are all real things you can run. All right, you guys, same idea over and over. Okay, so this is a little bit more complex. You can have two inner queries as well if you want, okay? To make it more and more complicated. So please read it and then understand, but the idea remains very simple. So one last time, what it is the inner query cannot just finish running only one time and then the outer query finishes. It's not like that at all. The outer query has to send some data ls to the inner query. Inner query takes the one ls and compares again the whole table with ls to see, are you true, are you true? So we call each row of ourselves the inner variable LA. And this is like I, this is like J. So run and then give me a result. Now only the top row is done. In the for loop, the outer loop ran one time. Now the outer loop has to run the second time. So I step to row number 2. I give you data for row number 2. So you have to run through all the columns and do something, give me a result back to me. So it's a double for loop is all. Okay, so if you want to go crazy, make a situation where you can have another correlated subquery over here. That's possible, right? So then what happens? What if you do that? What would it be called in 3D? So main query like this. So then the main query has a subquery, and the main query has to send the first row of data. Subquery has to run, return the result. The main query sends the second row of data. Subquery runs, return the result. Main query gives me third row of data. Run through all of it, return. So I'm stepping row by row by row. Every row, make you run again. What if I then do the same thing here? So every time this has to run, right? I take some row of data from me and I send it to a subquery here. So then this has to run, then send the result back to me. And then I give you my next value. You have to run again, send the result back to me. I give you my next row. Then what does that look like? What does that look like? Anybody? So again, exactly, that's all it is, right? So I have basically this is what we're saying. I'll use 3 different colors. So what I'm saying is already you have a situation where this is passing data, this doing things, sending it back. It's like a double for loop, row 1, row 2, row 3, what. So each row is making this run many times. But now I can turn around and do the same thing to somebody else. So I can then make another sub table right here, and then I can do the same, right? So every time somebody sends me one row of data, right, I need to go through all my rows. But then each one of my rows, I can send to here. And so then they have to run through all of their stuff and give me a result back. Then I'll take this and then send it to you. And you have to do all of that and give it back to me. Then I'll send you this and give it back to me. So I need to keep sending you data. Then when I'm all done, I'll send my data back to you. Then you would do the same for your second row, send it to me, but I'll take that and then make you do all the work. And then take the next and make you do all the work. So it's basically a 3-layer loop. It's a triple nested loop, right? So it's a for I equal to 1 to 100, and then inside that for j equal to 2 to 500, and then one more time for k equal to something to something. So triply nested for loop. But that is totally possible to write in SQL. Okay, it totally works. So please come up with an example of why you might need that. Meanwhile, let me ask you. In an image, this is 2D, so I have a pixel operation, right? Very simple image. Just blur the image. What would a 3D version of an image be called? Like what if I have the third axis, right? The third dimension. Then when I look through all of them, so what is that thing called in CS or in graphics, in general? Yeah, pretty close. It has the word VO, but then it's not volume. Pixel, like what is exactly voxel? Yes. So voxel is a volumetric, pixel is a 3D. Minecraft, okay. So Minecraft, all those little things the characters are made up of, they're called voxels. And we actually use them seriously, in graphics and other things. Voxel processing is more than just Minecraft. We'll very quickly just do voxel Minecraft. But we can use it for doing CAT scan processing, so for medical data. So all of those are voxels, okay? So it's all just voxels. That's why voxel brushes, voxel hammers, voxel this, voxel that. The whole Minecraft world is basically just being processing of voxels. When you like chip away at something, actually deleting voxels, okay? But you can actually do voxel processing of CAT scan data, because voxels are how your X-ray information is stored in your brain. Suppose you take a brain CAT scan, okay? Then the brain X-ray passes through your whole head and comes out and it's stored in a virtual cube that is surrounding you. Then you can take a cube of data and actually do processing on it, okay? So then say, like somebody's head is here, right? So then you pass X-rays from every possible orientation, but then all those X-rays are stored in a voxel grid that surrounds your head. Basically, have a little voxel grid. So then in the voxel grid, all the data that comes from your density, because you have bone, you have tissue, blood, what, right, and then your air. So all of those 3D pixels are all, those values are stored. And then that's basically a 3D map of your brain. Then you can slice that virtually and then see what the brain section looks like. You can spin it around. You can do like all kinds of cool things. Say there's a tumor somewhere, then the surgeon can actually cut virtually and know exactly what direction to insert the instrument when they actually do surgery for you, for real. And they can do pre-surgery planning. Okay, that's what this is. So I'm going to show it to you like that. See, you're just sitting there into brain data, and then you can now just virtually just slice it however you want in any plane, any orientation. That's what the scanner does, just sit there. So you have a 3D map of your brain like that. You can just cut it any way you want. Very neat. I'll just say CAT scan tumor just to show you. Okay. Yeah. So then, like that, suppose you find some growth, then the surgeon knows how to do surgery planning. Like that. See, that's the 3D part of it. You can spin it. Right, that's very cool. Yeah. See, Hamza is actually a petroleum engineer here. Cool, yeah, great. You can use things like sonar, right, and then actually image the underground and get exactly the same thing. So rather than the patient's head with bone, tissue, blood, right, fluid, cerebrospinal fluid, but instead now you're actually talking about oil, crude, or just rock or water. And then they all have different densities. So then you can image it and you have a map of underground, where the oil is. Like, wow, and you can drill exactly there at a certain angle, right? It's a great analogy. So that's what I meant right there. So you can do like math. So it's very cool projection operations going on. All right, so then what do we have? Voxels, extras, lectures. How do we get there? Yeah, here. And so 2 correlated subqueries. But those are 2 different ones. Okay, you can have different correlated subqueries. But the thing I started to ask you was, how do you cascade them one more time? Then I can have a triple one. In fact, you can have both, meaning this can be a standard double correlated, and you can have an extra triple correlated as well. There's really no end to what you can do, okay? So the system allows you to do some very complicated queries. Therefore, to finish up our query stuff, it's like this. So select columns. These are called column subqueries where they generate new columns. These are from subqueries where they generate new tables whose values can be used in the where as well. This is the one with the CP1 and CP2, okay? And then the usual wheres, mostly where the select subqueries go. But each one of them looks like that, meaning they can never select something from something, where something. So there's a cascade of 3 raised to n operations. So this is 3 raised to 1, right? That means there are 3 pieces. And if each one of them have 3 pieces, then in the next set, I'll have 3 squared. I'll have 9 pieces, right? And then 3 cubed and 3 raised to 4. So it's like 3 raised to n. Just somebody's trying to ask me something. Yeah, so it can get quite complicated. All right, so now, just to finish all this up, SQL functions are pretty simple. There's 2 types, the types that we write and the types that come with the implementation. These are the things that come with implementation. I already told you, things like string library, date library. So we don't need to spend time on this. Okay, you just look it up and use it. Because functions return a value, you can use a function anytime a value is legal. This is like standard programming, right? A variable equal to, value like I equal to 5, or I can say I equal to square root 5. Because you hope that square root function will come back with root 5, 2.23 something, 2.26, I guess. Yeah, so then those ones, wait, square root to 1.414, what am I saying? So those value, sorry, I'm just obsessed with root 5 for no reason. Yeah, 2.23. I was right initially. Okay, so then, that can go into a variable, right? Because then you can write something equal to something because functions come back with a value. So the function or even an expression, you can do expressions. They all replace themselves with a value. So in the end, you can do like all these crazy things, but hopefully as long as they all turn into a single value, that value can be stored in a variable. So exact same thing in SQL queries. So queries can have functions in them, but if the function comes back with a value, then the value would be used in place of an actual number. What is actually a number called in programming, or a number or an actual string? Like what would you call the string USC? What would you call the number 5? It's a programming term for it.
Variable or constant?
Constant means you would not be able to change it.
Literal. Yeah, literal.
Very good, exactly. Because say in the string, say you want to reverse the string, right? You should be able to do that. Yeah, so it's called literal because USC is literally USC. 5 is literally 5. So that's a literals, exactly. So, so a variable can basically hold a literal or it can hold an expression. So SQL functions are basically expressions. Okay. So functions have to compute. Functions can be combined into bigger expressions. All right, so these are the built-in ones, okay? So absolutely no comment at all. Things like conversions, you can convert from dollars to euros, things like that, some standard things that make sense. They come with like many database implementations. The best part is you can write your own. If built-in functions don't help you, you can write your own regular expression function. You can write your own any kind of complex stock calculation if you want. So this is all completely open to you. So we'll come back to functions in just a little bit. Meanwhile, just some very basic things like how do you do union? You've seen union examples before, just visually. What if you want to combine all the Keck students with the Viterbi students? Then you would do a union operation. If you want to know who goes to both schools, who only goes to one school. So you can do all of them. And then for all these three things to work, obviously the column names and the column types would have to make sense, right? They have to be identical. Otherwise, how can you even do a union? That condition is called union compatible. So if one table even has one extra column, the other table doesn't have, it's not union compatible anymore, all these would fail. So what would you have to do to get rid of that extra column? How do you keep only the columns you want? What is the pre-processing operation? Like what is the SQL command called?
You do a select with the specified columns.
Yes, exactly. So mathematically CARD called it project, right? But SQL does not need a project keyword. It's basically select, Yeah, so select just the columns that you want. I'll leave out the column that you don't want. Okay, so afterwards you become union compatible. Then you have a union that's possible. Again, all those are possible. They're like data flow, right? So any table, say there's a table, and the table will say with one extra column you don't want. You can pass it to a select operation that gives you only the table that you want. So then that, and then in the meanwhile, the other table that you already had it the right way can then be sent, both of them can be sent into a union command that can then do a union and give you a long table with both of those. Then I can do some kind of a join operation with some other table. So then there's a join operation. And then I'm going to get one more table as a result. So the crazy thing is I can build all these tables. Then I can split the table up into two parts, do a select with only this one, and again, do a select only with this one. Then I can split. So I can use SQL operations to do all kinds of crazy operations, okay? I can do something different here, something different here, and maybe put them back. So I have a tree of operators, like a graph. I mean, it's really a tree in the sense there's no going back. You don't join it back. Okay? You don't do like weird loops or anything. It's strictly an operator table, an operator table. And then in the end, you get your final result. That's called data flow. Because data literally flows through all the operators. Cool. Okay, so then that's possible. Union is just one step that you would do. So then look at the union examples. Union all, by the way. So in the union, in the USA example, if some students go to both schools, right? If you try to union them, that student's name is in both tables. So then technically they exist twice. But then that's not a valid table anymore because, the entity, the integrity is lost. The primary key is identical. The whole, everything is identical. So in a normal union, you wouldn't want that. Normal union is smart enough to throw away duplicates. But if you want to see who the duplicates are in the union, then you can say union all. So then you will actually get duplicate rows, but it's not a valid table anymore. You can manually go and delete that if you want, or change the keyword. But it exists if you ever want to look at it. It's called union all, okay? So intersect is pretty simple. It just tells you what's common to two tables, possibly a null set. Nothing needs to be common. And except or minus, this is the only one that is not symmetric, meaning A minus B is not the same as B minus A. So order matters. Whereas in union and intersection, order doesn't matter. And then, instead of intersect, you can do things like, in, not in, right? So why would you do that? So what is A intersection B? Like, how else can you describe A intersection B in terms of things like differences, right? So if you want just, A intersection B, right? So what would that be? A intersection B. In terms of other operations, so what would intersection be? Anybody? I just want the intersection operator. You can say things like, in and not in and stuff like that. Can you do it with ins and not ins? Just want the intersection.
In or join?
That's a different concept. Just think only in terms of sets, okay? So a set union is all of them. So a set union is really A union B, right? But A union B can be thought of as A minus B. So A minus B is only one part. So this part is A minus B, right? This part is A minus B. And likewise, this part is B minus A. Okay, this part is B minus A. And this part is A intersection B. This part is A intersection B. If you union all of them, you will actually get A union B. Union all of them, then you will get the grand A union B, right? So then in terms of all of those, maybe it is possible to express Yeah, A and B. So can you actually say A and B? That's really very interesting, right? Okay, so what about some rows of A that are literally in B? Is that possible? So that's basically the answer, right? We're trying to say, how can you use the SQL in operator to actually get something like an intersection? So that's literally, things that are A that are actually in B, right? Or what about B in A? Can you actually say B in A for this or not? B in A. That's also true, right? Yes. So then the same thing is also B being in A. So please try that, okay? It's actually very surprising. You can use like the in condition, the in keyword to be able to, use the intersection. So if for some reason intersection is not available, or there's an interview question, how would you do intersection using ins and not ins? You can answer that. 651, okay, this is good. All right, virtual tables. So this is when I told you any subquery that you run or any query for that matter that you run, if it results in a table, right, then the table can be actually stored. Then that's called a material view. A material is something that's real, but you can make it real. But otherwise, until then, it's a virtual view. I don't even have to say virtual view because views are always, these tables are always virtual anyway. It means they exist in memory. When you shut the machine down, it just goes away unless you want to keep it, stored in disk. Okay, so let's start by saying it's a virtual table based on a select query because all selects become tables. Tables can be empty, or it can be one row or even just one single cell of data, but technically a table, okay? Okay, that tables, all right, okay. So then base tables is the initial table that you put in the query from which these views happen in the first place. So then if you want to actually give these views themselves a name, meaning if you have a big SQL query right here, I want to call the SQL query something and do more queries on it afterwards, like basically like creating a variable. It's called create view, okay? So you add the word create view and then give the view a name, like a variable name. And afterwards, say as, and then go to town, meaning do everything that you've done so far in the SQL lecture, all of it. Because when that comes back with any table at all, then the table would then become this view name, like a new table that you create. And afterwards, you can write more SQL queries based on the view name. And at any point, if you made a view with a view name, you can say store the view name on disk as if it's a real table. That's when you call it persist, or it's called materialize. When you materialize a view like this. So materialize a view, just a SQL. Then it's called materialized view. It's when you create like a real table in memory, basically. Okay, so it persists the data returned from your definition, like all of that. Cool. The nice thing is, the views will also change as, the underlying queries change. So if the underlying data values are changing, and you run this query over and over again, then the query's result, which is the view, will also update. So much like a pointer, to the actual tables that are doing the results. Okay, but you can read up on this if you want. View. So the view would disappear, and this is actually permanently stored because sometimes you don't want to repeat the commands. All right. Then, in other words, do all you've done before, but add this extra part with the word view. So I'll show you an example, like here. Suppose you have a view called price greater than 50. For some reason, you wonder, too many times per day, how many things cost more than 50 bucks? Don't keep running the same thing over and over and over again. Just make a view and maybe even put it on the disk, okay? But at least call it something. So price greater than 50, so this new line you glue on. And from here on, things you've seen before, this like pretty trivial SQL. Tell me the product description, product quantity on hand, the price from the product table where it's more than 50 bucks, literally so simple. But now we have a name for it, okay? So then it says view created. How do you know all this worked? Just say select star, and then you get your list. It's like, just to make sure it works. But rather than select star, you can do more things. You can say select description from this where quantity on hand is more than 10. Then you will only get these values, right? Because this becomes like a real table at this point. It's becomes like a real table. So yeah, sure. So if you drop the view, then it won't be stored in memory anymore. In other words, there are two steps. One is you can hold the view and do calculations all day long and then delete that. Or you can do a material, in which case it can go to disk and then you have to delete the table. Cool. Just like drop table, like drop view, you can drop table. Good. Sequences are just simply built-in numerical values. So if your primary key can be as simple as 1, 2, 3, 4, every time you add somebody to a row, right? Then you just want the row increment to automatically go plus plus. Then you can call them sequences. So then the sequences can be given a name, and then the row ID can basically become the sequence name. You can create as many sequences as you want. You can also delete them. So now it's like more and more like programming. And sequences have nothing to do with the table unless you associate the sequence with the row ID. They're independent objects. And you can do a sequence plus plus anytime you want. Just think of it like a variable, and you can anytime tell the sequence do plus plus. And then you can shove the value somewhere in some other column, not even the primary key column. You can have some random column R, and then take the sequence current value with the plus plus, and then put it in there. So I'm going to show all this to you. It's not tied to it unless you would use it like in a value. Create, you meant that you said you create. Oh no, sorry. Yeah, persist is something else. So persist is when you actually create the view on disk, okay? So you can look that up.
Oh, yeah.
Independent objects not tied, neutral value. Yeah, so then this is the part where the table attribute, mostly primary keys. If you're too lazy to make a primary key and it doesn't matter, just a row ID can be a primary key. Then you can use a sequence for that. So how do you make sequences, right? Look at this. Oh, sorry. Okay, so just say create sequence. So these all look like programming languages, right? So create sequence, and that's the name of the sequence. You can start the sequence with any number. You know, when you order checks from a bank, okay, when people actually used to write checks, you would run out of checks, and so your check number that you're tracking in your own personal finance inventory. Say your last check that you wrote was 3999 or something. Then you can tell the bank, please print me checks starting with the number 4000. I don't want to start with the number 1 anymore. That's exactly what this is. So I can start with, this no cash, don't memorize it. It's literally no cash. So this is starting value. So I can have a sequence with any starting value that I want. And that'll be, it's like initializing a variable, int I equal to 20010. Then I can do plus plus I. So that like this. So here we select two sequences called customer code sequence, invoice number sequence. This is literally for how many invoices people ordered from us. Say the last invoice was 4009. Now you start from 4010. Okay, so then the max value, min value, these are defaults. But so the last number, which is really the number you start with, because usually they start with 0. Okay, you make a sequence. Now what do you do with it? You can do this. You can say make a new customer with that sequence that I just now made. Okay, so look what we're doing, like next val. So these are members that are automatically incremented for you. So when you say sequence dot next val, there's two values called cur val, next val. So when you say sequence name dot cur, cur val. So cur val means the current value without any increment. Next value means the value after you increment. That's very interesting, right? Actually, wait. Next value means take the current value, use it, and then do a plus plus afterwards, like a post increment. So I'll say this one more time, okay? When you say the word cur val, the cur val is used, but the sequence will not change at all. Next time you say cur val, the same value is going to be used. But if you're going to use it for people, you want this number to change. But you want the number to change after you use it, like a post increment, not plus plus I, more like I plus plus. So because we said you start with 4010, then that value would be actually here, 20010 would be used. But after that, as soon as that value is assigned, the next val, because you said next val, will change that to 20011. Then if you say next val again, the next customer gets 20011, and it'll change it to 20012. Okay, so you'll use the value and then post increment. Okay, so next val, like this, you can actually see it. So next val returns the current value, then does plus plus, post increment. Again, there's a huge difference between saying plus plus I versus I plus plus. So pre-increment, post-increment, this is what sequence does, post-increment. Then you can actually see it in action. You can do a couple of those and see that it actually works, like here. So cur val does not do anything. Cur val just keeps giving you the same value over and over. All right, so obviously when you insert people, you want to do like a next val. All right, so do a next val one time, and then see what happens. So do a next val, like here. First of all, you do it one time and you see what happened. See that value that we started the sequence with got used. But if you do a next val again, then the next time it's going to be like 1, 1. And then in the meanwhile, do an invoice. So do the invoice number, and then this invoice number, and then do a cur val. So in the same invoice, suppose you want to insert multiple items, you keep saying cur val, all the line items, right? They come from the same invoice. Then they all go into the different line item, but then the invoice number remains the same. But then if you want to add more people, then the next val would increment that. Cool, right? So you have two different examples. So what we're saying is we keep saying cur val over and over because you don't want that item number, invoice number to change, because the same person ordered those things. So you want that to be the same. Then you say cur val. On the other hand, if you want to use them like a primary key, you would say next val because it'll use the number and then behind your back to a plus plus so that it gets you the next value. As far as I know, there's no plus equal to. You cannot skip 2 or 3. Actually, I don't know. It's always been, in my opinion, that you can only do like plus plus. I think that should be enough. All right, so moving right on, a little bit more programming. So we call this procedural language SQL. You can Google the words PL SQL. There's even a trademark for PL SQL, okay? But I don't imply any trademarks in any of what I'm saying to you. It is just a conceptual idea that SQL can be more like a programming language. So on top of all the things we've said so far, with everything here, so SQL can do a lot. But in addition, can you also can you write real functions with it? Can you write like a procedure that is a bunch of code with a name? So then every time I type that name, all the code runs, but it does not return anything. Can I do cool things like that? And the answer is yes. So then that is what together is called procedural language SQL. So it's not a product or anything. In other words, every database supports this, in some form or the other. You just have to read the documentation. So in PL SQL, you can do looping and branching. That's pretty cool. So now it becomes like a real programming language. Even better, you can actually hold data in variables. So you don't have to repeat the same data over and over again. And then the best of all, you can actually do functions and actually call those functions with your existing SQL code. You can write your own function that does standard deviation and then run it on the GPU column. Then I can know what you guys' standard deviation is. That's pretty neat, right? Because you cannot do any of these things in plain SQL. It just augments SQL. Okay, we call it PL SQL. The examples I'll show you right now are this. You can have an anonymous, like a JavaScript anonymous function, do a block of code, and then just run it one time, and nobody knows. The engine does not know, you don't know. The code just went away. It might be useful, once in a while, just a block of code. I see. So why is that? Was it like pretty intricate to change, or it's pretty funny? Yeah, those things are written by senior SQL programmers, right? And they work so well. And actually, people tell you, don't touch it. If you try and modify something, it'll probably screw something up in a bad way. Just leave it the way it is. It does data warehousing, right? Collects like all kinds of crazy data, cleans it up, and does magical things. If you mess up, your data warehouse is going to get screwed up. So people just run it. That's probably why. Okay, so a block of code is an anonymous, just a one-time block of code, right? You never see it again. Not really useful. We'll come back to triggers, but I'll tell you about this. This one is a block of code, just like this, but now it has a name. Then I just, next time I simply do execute, followed by the name. And the name would go and run all the code that you wrote for the name. Like put things on sale, for example. Like anything that is less than $10, suppose you want to put it on sale. You can make a little procedure for that. It doesn't return anything, okay? Just does it. Goes and alters your tables. Then that's a cool procedure you can have. On the other hand, tell me like how much inventory is in my store right now. Like I add everything up. I can make a little function for that. And the function can return a value. And I can run that every hour and put that in a new table. I can insert that value into a new table. Then every hour I know how my store is actually changing, like how much money I'm making, losing, right? Jeff Bezos probably has one of these on his large screen display in front of him, put his feet up, watch the money go up. But then you can have a stored function for that. So the difference is function returns a value, procedure does not return a value. It's pretty simple. So I'm going to show you all of these. Triggers are very, very interesting as well. A trigger is literally a cell level callback. It's exactly what it is. A table cell level callback, meaning I can write some code and attach the code to any cell, meaning to any row or any column really. And then I can tell that cell if the value changes, if any value in a GPU changes, let me know, GPA. So suppose I'm looking for students who are more than 3.95, okay? Then students' GPAs change all the time. So I can have a trigger attached to the GPA column that says anytime, new value occurs, the value is more than 3.95. I don't know, just send me a piece of text. It's possible to do that. Then it's like a watcher. That piece of code is just watching what happens to that column value. And then it could trigger something. You can even trigger some SQL. That's why it's called a trigger, based on that condition. Suppose the column is quantity on hand. And suppose you have a Q min. So this is the minimum products that you would have before you have to reorder. Suppose Q min was 5. This is the gallons of milk. This is the gallon of milk. And say the quantity on hand went down to 4. Because say you had 8 gallons of milk. Somebody went and bought 4 gallons of milk. So now 8 minus 4 is 4. But now the 4 is less than Q min. So I can have a trigger for the column that says anytime the quantity on hand goes less than Q min, and if the product is called milk, then automatically place an order. That's pretty neat, right? So therefore, automatically the checkout counter can actually place an order. So that's very cool that you can do triggers like that, just watching every cell. And very nice. Yeah, nice. Your triggers are actually quite neat. You can actually watch it work. I'm going to show you an example here. All right, so all of those are together called procedural SQL. All right, so ignore all the PSM stuff. I was going to say crap, but some of these are Oracle trade names, okay, so we don't care about them. But the idea is that they behave more like programs. All right, so you can do blocks, triggers, functions, procedures. Those are the 4 things over and over. So I'm going to show you. All right, a block is just a block. These look like old-fashioned Fortran programming on an IBM mainframe, IBM 360 in the 1960s and 1970s. Oh my God. It's literally a character terminal where you would say the word begin, and then you would do whatever you want to do, and then you say end. And after you say slash and enter, slash is pretty much like run, then this little thing would run. It's almost like pointless, right? But it can be used for tracing, one command at a time to see if your command succeeded. So tracing is literally something that you print by saying server output on, like set trace on to like info. You have info, debug, error, all that, right? So set it to like info level. And then do your little document, the update like this, insert, updating, putting Bill Gates in on the nicer case. But now you say put line. If you don't have a put line, then you won't see the new vendor, okay? When you say server output on, that put line would actually work. In here, we're not doing anything, so we don't know if this worked or not. That's basically what we're saying. But now you can watch it. But the main thing is you can see what happened. And then you can see that the names are added. 25678, 25772. Both of those got added at the top. Okay, so then it means an anonymous block of code is working. You would use it just to simply, you don't even have to name what this is. This just means I'll go in my shell and just type 1 line of SQL and just run it right there. That permanently alters the table. It does a commit operation, by the way. If the operation succeeds, then it'll actually write this to permanent storage. All right, that's all it is. So it is just simply, the chance to like run SQL one at a time. What else might you call this in a standard programming language? So what if I walk up to a terminal in JavaScript and just type a couple of lines and I run it? Then what is such a terminal called? It is not an IDE. It is not a shell. Okay, those are different names. It's a different name specifically for running code like 1 line at a time. I run something, I get the answer. Then I run something else. Very nice, fantastic. REPL. It's a REPL. Read, evaluate, print, loop. So as soon as I type and I hit enter, it reads it, evaluates it, runs it, loop again, keep on looping. So it's a REPL, okay? So that's all we're saying. So if you have a SQL REPL, and every SQL does come with a REPL, the operations you do on the REPL, they're just simply called anonymous blocks. Because until you hit the slash, it won't run. So you can have multiple lines, okay? You can have like 1,000 lines if you want. But then you're done with it. Okay, so triggers. Triggers are, again, code, meaning SQL code, that are automatically invoked. So here's the difference. Like a callback, right? All UIs automatically invoke code. See like this. If I hover over plus, then that happens. If I click on this tab, the tab is going to show up. So UI is all done like that. The code is just waiting for me to do something. If I click on this, desktop is going to open. If I click on this, it's going to open. Whole world works like that. Okay, we call them callbacks. We call them event-driven callbacks. So triggers are also event-driven. In the sense, the events are something is changing the value. The trigger code is going to kick in. In fact, speaking of events, something called triggering event, like what can cause a trigger? Is it an update for a cell, or is somebody trying to delete like a whole row, or even a column maybe? Those are events. So timing is, do you want the code that the code is that you're watching the value, you want the code to actually run before the cell is actually updated, or do you want the code to be run after the cell is updated? So depending on the cell update, you can actually do SQL to some other rows. You don't have to do something to that one cell. You can do operations for the rest of the table. So do you want to do it before or after? So I'm going to show you examples for all this, okay? And then also, do you want to do these operations, depending on what this is, on only one row of data, or maybe on a few rows, as opposed to the whole table? So that's called triggering level, okay? So then therefore you would define a trigger, and as soon as the definition is end, you start to run, the trigger starts running, and these things will happen. If you are tired of the trigger, you don't want the trigger to run anymore, you delete the trigger, then it'll stop running. So triggers can come and go, it's up to you. Good time for an example. Okay, so before, after, it means again, in this case, so the triggering statement. So when will the code execute? Based on like what is triggering it, would it execute before or after the thing that triggered it? And then the event literally what is actually triggering it. Is it an insert statement, update, delete? So what this means is anytime, something goes into the Amazon bucket, you can be told, you can be sent a text message. If someone updates a picture to your database that's on the cloud, then you can get some notification for it. Conversely, if somebody deletes something from your table, you can be told. But more commonly, if somebody modifies something, then you can be updated. Because the callbacks, it's called payload. Like, what is the actual trigger definition? Can do anything. Can do lots of things beyond just standard SQL. You can update. Okay, so I'll show you some examples. The levels are pretty simple. So this is when you say statement level, that means basically for the whole table, for every row. Otherwise, you have to say row level. Okay, so it's the other way around. Sorry. So statement level is if you don't say for each row, it runs out the one statement that triggered it. On the other hand, row level is for each row. So this is the whole table. It's one statement. All right, so now it comes time to how do you define that? It's pretty simple, like this. So the syntax is create or replace. Usually never replace them. This just simply means, say an old trigger was running, you can overwrite that code with some new code. Just call it replace trigger. It won't give you a warning that says the trigger is already active. Just silently overwrites it. So create or replace trigger, the name of the trigger. Before, after, this is the exactly when do you want the trigger to happen, and what condition for the row triggers it, on what table the trigger is happening, and then do you want it to be run for each row for that whole table or not. Leave it out if you don't want to. And then you can declare some variables, like a little function block. Declare some local variables. The variables can be used right here in the trigger. Use a standard SQL, okay, begin, end. But you can have function names and procedure names. We haven't talked about it. How do you write a function? So those can actually come here, and that can all be together called the trigger name. So as soon as you say end and you say execute, the trigger kicks in. So how does the trigger actually work? We'll see it, okay? So you run it. This trigger is very interesting. This says, like I drew the diagram, reorder flag. When it's 0, it means don't reorder. When the flag is 1, it means it's time to reorder that. So at the end of the day, at night, the store manager can do a query when they say pick out all the products for which reorder code is 1 and place an order automatically, just hit one button. So how do you go from 0 to 1? This happens. So usually by default, everything is 0. After you reorder, stocks come in, you set that flag to 0. So it's 1 only when somebody bought so many things, eventually you go below the minimum, you dip below the minimum that you hope to have in your store. So every product has a minimum that they carry, and once they go below the minimum, they'll reorder. Okay, so say you have a trigger like that. How do you see it actually in action like this? Imagine your hardware store. You have 8 quantities of this power painter nozzle thing that people use for painting the walls. And then your rule is below 5, we reorder. And every time you reorder, you get 25. That's separate. Okay, so it's not time to reorder. So I walk in, and then I buy 4 of those. So then now the quantity on hand has gone to 4. So the reason why this happens is I went and bought 4. Okay, so then this is now 4. And because it went to 4, the reorder flag automatically kicks in. How do you know that? Just look for it. So now the quantity on hand is 4. 4 is less than 5. Therefore, the flag has been turned on. So the next step after this is to actually place the order and turn it down to 0. And if your minimum is 25, then maybe 25 is going to get added to 4, become 29. Cool, right? That is exactly how a trigger works. Okay. So if you don't want to trigger anymore, just say drop trigger, then your trigger deletes it. Trigger, that's funny. You should drop trigger as well. If you drop the trigger, then it's deleted. Okay. And then stored procedures. So this is when slightly nicer than just an anonymous block of code, because this block of code you can run as many times as you want because it is stored on disk, okay? It's called a stored procedure. It's not a function, so it's not going to return anything. Otherwise, it looks almost like a function. You can have variables that's passed in. No, there's a block of code. All right. So in here, code sharing was the main thing in here, okay? So rather than many of us write the same code over and over, then you publish documentation that says, this block is available if somebody wants to run it. That's what it's called. And then the whole place can use it. Okay, so again, how do you use it? Create or replace. Looks a lot like a trigger. But now you say the word procedure, name of the procedure. Optionally, you can actually have variables that go in and out, okay? But this is not a return, by the way, okay? This is almost like in C++ using reference variables and pointers, okay? Because it's not an actual return. It's like secretly returning basically out through the indoor, Led Zeppelin had an album called In Through the Outdoor. So it's opposite, out through the indoor. Then those are called in-out data types. In other words, mostly in a function, data comes in, like values come in, and you would use it. But secretly, if you modify it, then you can call it an in-out type. Okay, so it is not true that procedures cannot return. Procedures can return output, but mostly you don't do it. It's weird. Make it a function. All right, moving on. See, if you have a private block of variable declaration, goes here. But this is where the statements go. Like here, create or replace procedure. So I want to put things on sale, okay, like this. So how do you put things on sale? You say begin and end, update product, set the discount code to be that discount code plus 0.05. So this is how many dollars off or how many cents off, okay? So every time this runs, we're gonna put 5 more cents off. The product is getting cheaper and cheaper. But on what condition though? The quantity on hand must be more than twice the minimum. It never falls to the minimum because nobody's ordering it, okay? So say the minimum that I want to carry in my store is 5. So 5 times 2 is 10. So anything that is more than 10 units, I'm going to assume at the end of the day that nobody bought that during the day. So I want to put only such products on sale and see if people would then buy it. So every time I run this code then I'm losing 5 cents because the discount is going up by 5 cents. That's a neat procedure, right? So I want to run this over and over. I don't want to look at this again. I just would type exact purchase product discount, and then this will happen. I can do it how many times I want, and every time I lose 5 cents, 5 cents. So like this. It's a fun little thing to write. And try it. Okay. So again, at the top, so imagine the thing was already written, right? So you have all these products, and then some of them, for example, are like that. For instance, this one is way more than 2 times minimum, right? Because 29 and you're supposed to only have 10. So, but others are not. So 8 is not more than 2 times 5. So you don't put all things automatically on sale. When I run this, when I say exec, the name of the proctor, then look at the result, see what happened, okay? So now you see those things now have an extra discount, okay? Initially there was no discount at all. Now it's 5 cents off really. So if I do it again, it'll be 10 cents off. It'll be 20 cents off, 15, 20, keep going like that. But only the ones, that already, had, like, look at this one. This one was exact, so this is 5 times 2. But then, it's not greater. Therefore, that also went on sale. So the 10 cents now became 15 cents off. Okay, so it's basically working. That is the advantage of this. You can modify tables with just one word. You don't want to look at the SQL over and over. In reality, there's a button that some product manager has. You just click the button and it does it. Okay, that was cool. 718, going on. We're pretty close. Okay, so a function can return a value, okay? So the main thing about the function is it's going to look so much like the procedure or the anonymous block. They have begin, end, but this must necessarily have a return statement, just like any function in the world. It cannot be void. It does actually have a return type. And so the functions can be called by other procedures. So the procedure can call a function. And the function can also be called within triggers. So the main reason actually to write a function is to make triggers simpler. Okay. So function, you say very similar, say create function, not create or update for some reason, just create function and the function name. And now the arguments are hopefully very useful, right? Otherwise the function is going to return something, you have no way to control it. So most functions will have an argument, things that are coming in. And then like C++, you have to actually do the return type. You have to say int space, something, the count. The return type must be declared and have to say the word is and then begin end. These are like old fashioned programming really. Wow. And then the function is created. You cannot anonymously execute like JavaScript. You have to do it separately in a trigger or a procedure. That's the point of doing it. So the function looks like this. Again, you can go to tutorial's point. Now we'll look at lots of examples. Literally, now is A more than B or is B more than A? Find max, find the bigger off. You can make a little macro, right? Pretty simple. But say X and Y come in, X is a number, Y is a number. And the function has to return something. Literally an if statement. If X is more than Y, then Z is what you're returning, by the way. You just return Z at the end. So then Z would either be X or Z would be Y, literally depending on the if statement. Just like a weird little function. But now you can run it, by the way. So once you write a function called findMax, then you can declare these variables and put some values into them and literally do a findMax, and you will actually see. Wow, such an old-fashioned way of doing it, right? These days in like Python, JavaScript, you can do all this in one line. Yeah. Is it possible to return a table? Good question. I don't think so. It's a great question. Functions are usually, relegated to like pretty simple return types. If you want to return things like tables, right, you can write more complex, SQL code in like Java or C++, and then you can call it separately. But as far as I know, the answer is no. That'd be pretty cool, actually. This is why SQLite is actually helpful, okay? If you want to actually return a whole table full of stuff, just do it in SQLite. And then you can use the binary format for directly outputting the table. Wow. So no SQL, nothing. It's possible to do that. Really cool thing to do. Okay, so that was the end. Wow. This was a lot, right? But at the same time, not a lot. This all makes sense to you. So if you really had never seen SQL before in your life, like, wow, none of this is particularly difficult. It can be complex, which is a very different thing because you pile on more and more and more things, right? And 3 months went by, and you have these massively cool queries. It took you 3 months to write. So no one can come in and say in 1 second, I understand what you did. Probably takes them 3 months to get it, right? But that's totally okay. Otherwise, every single step that you would use to get there is not hard. None of this is difficult. So we'll just leave SQL at that. I think your SQL homework most likely might involve you going back to your table diagrams and making them be real. Actually create tables and actually put data into them. And I'll ask you for some queries, and then you should write some SQL to actually go in your tables and output those queries. Then your tables become real. Either that, or I would do something entirely different, which is not connected to your tables at all. So not decided yet. The Schrodinger's cat is dead and alive. Okay, it's only 7:22 after all, which is good. I still have one more cool thing to tell you, okay? We'll take a break probably at like 7:35. But let's start our next thing, okay? This is like an easy topic as well. It's a very important, easy, fun, cool topic. First of all, we should all take time to, be centered. So we all just close our eyes and go, oh. Oh. What the hell? You cannot see me, but I feel so peaceful, man. TM. What does TM stand for? What did we just do? Why the hell is the Buddha there? What is TM? Yeah, that's the T part of it. You almost got it. It's actually transcendental. Transcendental. What does M stand for? Take out your yoga mat. Close your eyes. Deep breath. Out. Meditation. TM actually stands for Transcendental Meditation. Why am I telling you that? Why not this time? Okay. TM Maharishi. Yeah, she's the one most known for that. It actually is. And Om is actually cool. Meditation absolutely lowers your blood pressure, even your heart rate. The brain waves and slow down your thought. Yeah. It's biofeedback, I think is really what it might be, but it's cool. Okay. So while all this comes up, you can read about it. It's real. Transcendental meditation. TM. This guy popularized it. He took Beatles to India. He had an ashram way up in the foothills of the Himalayas. And the Beatles went there and stayed for a few weeks and made crazy albums like the White Album and Abbey Road. Okay. Read about him. All right, so then why the hell is that connected to databases? Because TM also stands for transaction management. Cool, that's why. Look at this. I'm not what you think I am. You are what you think I am. Ooh, deep. Mind blowing, man. Okay, so we only have 30 slides. And it's simple. All right, here's the cool deal, and this is all real. When we go to Amazon Live and start ordering things, how the hell, say we're ordering the Alienware laptop that I almost bought. So say you order this, right? It might tell you how many are left actually sometimes. So then how do you know, say it says 10 are left, more coming soon. If 100 people all click on the same 10 is left, but they all don't know each other, right? All over the world, 100 people click on it. There's only 10 left. Of those 100, who's going to get it? Or even more importantly, would all the 100 people look like they got it? Would the shopping cart actually process all the 100 orders and give them tracking shipping dates, right? Which is totally bogus because there's only 10 left. Will that happen or not? Okay, that's the question. Or I guess flipping it, how would you make sure that that does not happen? How would you make sure that multiple people in the world, that means today literally the entire world shops on Amazon Prime, is not buying the same 100 rolls of toilet paper, but 10,000 people in the US want it? So how can we prevent data from being overwritten by somebody else's transaction? It is that simple. Yeah, a little like that, exactly. So then the techniques for doing stuff like that is transaction management. So transaction is a series of reads and writes on a whole bunch of tables together that make up a database. So database can be many tables. So look how many tables there are. So if for some reason, whatever the heck that I do, I start reading all this, it touches many tables, right? Then what is called a transaction is all the things that I do as part of my operation, my buying it or my posting some new question or answering somebody's question or posting a new review or whatever, right? Or returning a product. All that is ultimately called a. I'll give you more information pretty soon, but just verbally to tell you, it is a series of statements, a series of SQL statements, and all logically belong together. It's like an atom. It's called atomic. So Greeks used to think that there's nothing smaller than an atom. They did not know about protons, neutrons. So an atom is unsplittable. It is as small as things get. That is what a transaction is. So a transaction is considered an atom in the sense that it really can be made up of multiple reads and writes. Like your transaction, whatever you're trying to do. But the thing is, the whole block of all those reads and writes together need to succeed or together need to fail. Like in other words, what is not allowed at all is some of those reads and writes to happen, and then something happens, like I lose my Wi-Fi, or my machine crashes, the battery runs out, the laptop blows up, or Amazon blows up. It doesn't matter. Something happens so that the rest of my transactions are not allowed to succeed. They fail. They fail in the middle. That is 100% not allowed at all. So the way you manage that is called transaction management, or like Karishma is pointing out, concurrency management, because concurrent means at the same time. So the question is, how do you prevent so many of us, literally millions of us, from doing the same thing over and over? It can be like all over the place, not just here. Uber driver, right? Exact same thing. So an Uber driver sitting there. So many people want the same ride. Okay, they're all trying to go home from the bars, right? And there are people waiting near the bars to take you home. There's only 10 Uber, drivers, and 100 people want to go home. So who's going to be called? In other words, who is the driver going to get? So the same problem over and over. Or only 300 airline seats to go to Hawaii. The airlines puts the seats on sale. $50 to go to Hawaii, over the weekend. Wow, 10,000 people in California want it. But only 300 seats are left, right? So how do you manage the fact that all the people are not able to buy the seats at the same time and show up at the airport? You go, oh my God, that by the way exists. Okay, there is such a thing. It is actually called overbooking. So airlines overbooking is a crazy thing that actually they do it on purpose, believe it or not. Okay, so on purpose, sometimes airlines will actually give you a seat number that is actually virtual in the sense that they gave multiple people the same seat number. They actually don't mind if you go up to the counter and bitch at them, because they're willing to give you a coupon for a future flight to make you go away, but they would rather do overbooking. It's pretty weird. Okay, look that up. Okay, it's a real thing. So what I'm saying is allowed on purpose to actually override each other. It's strange, but otherwise, in general, what is possible is for many, many, many of us, in fact, the entire planet, to click on this and read all we want. So there's a massive difference between reading a cell value and writing a cell value. Reads are non-destructive. So I can go and look to see what the ratings are. I'm not destroying anything. Okay, I'm literally just getting a view of data. It's totally fine. So many, many people can read at the same time, okay? But only one can write some cell value somewhere in some table at any one time, period. That is the end of it, okay? That's all. Like shared programming. So when you have shared memory, this kind of GPU core. And so the GPU core has some kind of memory that many threads are all operating at the same time. But then one thread, comes and writes that value, right, in the little cell. Only that thread is allowed to write the value, not multiple threads all writing, because they'll all lose each other's data, right? It's classic programming. So you have to have some kind of mechanism. Somebody brought up mutual exclusion, mutex, some lock, okay? So ultimately, I'll just give you the short answer. You can manage concurrent transactions, by locking. So you lock the one seat, the airline seat that somebody is trying to buy. So there's so many airline seats, right? They literally give you a diagram, and you click on that little seat. Then a clock starts ticking. It says you have 8 minutes to complete the transaction, because for those 8 minutes, they lock that seat and give it to you because you hope that you would buy it. If you walk away and get coffee, the timer expires, then your lock is gone. Then it goes back in the pool and somebody else can lock it. So only one person can lock it at a time, because it makes obviously the most sense in the world, right? Like how can two different people write the same cell? Because the last one will overwrite all the ones before. So that is the reason, that is all this whole concurrency management comes down to. It's a simple idea. Anybody can read. I can just look at the airline seats and go, wow, look how many movie theaters are the exact same thing. Fandango. I can go see every morning, wow, look at all the empty seats. So can you, so can somebody else, and what. It doesn't matter. But as soon as I want the nice middle seat in the theater, then hopefully I'm the only one that's going to sit there and watch the movie. That is all it comes down to, okay? So it's called read lock and write lock. Read locks can be shared. So read lock, you still have to lock, by the way. So even if many people are reading, this so-called read lock that is issued, that's really a very interesting idea. Because, somebody shouldn't be able to write while you're reading, okay? So reads are also lockable. But a read lock can be shared by as many readers as you want, okay? The lock is a shared lock. But a write lock, on the other hand, is what is called an exclusive lock, because, only one transaction can write that particular sum. So you have to lock it. So that's available only to one transaction. Many transactions can read. Or the third state for a lock is nobody locked it. There's no read or write. It's completely open. Okay, so then let me draw you a little diagram, and then it makes it all clear. This is like a little state diagram. You go from a completely open state to a read state to a write state. So only some combinations are allowed. You cannot go. Okay, so I'll show you. Suppose you have a completely unlocked state. The lock is completely open. Then somebody can then start reading, and you're given a read lock. And then a read lock can be, shared in the sense, read lock, they can lead to more read locks over and over. So reads can be shared. If you're unlocked, you can also become a write lock. And then at that point, you just stay right. If I'm a write, you cannot go to read, by the way, okay? So if I'm a write, you can only basically go back like that, okay? Like that. So you write, you finish writing, then you put it back, it becomes completely unlocked. Then you, can do a read or write. So very interesting transitions like this happen, okay? All right. So then I'm going to start showing you here. All right, so going right back, what is a transaction? Pretty simple. A transaction is a logical unit of work. It's called all of this because the whole thing must succeed or the whole thing must fail. So in reality, what actually happens is, while a part of it is succeeding, things are working properly, for no reason, no fault of yours, the rest could not succeed. The part that succeeded would be rolled back. It'll be undone so that overall it looks like nothing happened. The classic example that we use is checking account or a savings account. So I'm transferring money from checking to savings, okay, or maybe savings to checking. I want to pay off some loan. I want to write a check. Checking account, savings. Say I want to save money. I have a lot of money in checking. I want to transfer. So say I take $100 from here and I want to transfer it here, so that this is going to become minus 100. This is going to become plus 100. It's a pretty obvious classical thing, right? But what you don't want is for this transaction that subtracted 100, say you had $4,000 even. So you took 100, you want the 100 to go here. Say you had 3,000 here, 3,000. So the net result is it's going to become, 3,900. That's going to become 3,100. Transfer. But what you don't want is for the 100 to come off from here. So this becomes 3,900. But before it got transferred, something happened. 100 does not go here. So this is stuck at 3,000. This became 3,900. You lost $100. It literally vanished in thin air. That is not possible. See, if some transaction were to actually experience that, then this will go back, so you'll get your money back. So at no point will the database be allowed to do a part of a transaction, because the transaction is atomic, okay? That is called a guarantee, by the way. So the way these systems work, the Unix process work, they pretty much guarantee that the transaction will always be atomic in a relational database. In a NoSQL database, by the way, this guarantee does exist, but it's harder to come by. And the NoSQL world actually almost, unless it's money and some critical transactions, does not expect that at all, okay? Atomicity is a cool thing to have. Obviously, it's entity integrity after all can say integrity. But then the bigger point is, you don't want any mistakes in your database, right? You don't want to corrupt data. So the relational database pretty much guarantees atomicity. What is to the guarantee? It's a guarantee, which we'll get to very soon, right? There's four letters. Each is a so-called guarantee by the whole relational database system. And together it's called the ACID guarantee, right? So that it's called ACID properties that relational database has. And this is what makes relational databases so attractive even today, that if you install Oracle, Oracle will give you this ACID guarantee. There are 4 different things. They guarantee all the 4 different things. It means the data is rock solid. Nothing bad is going to happen to it. As soon as you go to NoSQL, you actually lose the ACID guarantee. There's also a 5th one, okay, called serializability. But there's not a 5th one separately, okay, it's actually these 4. So ACID. What does C stand for? If somebody already knows this. Atomicity, C.
Concurrency.
Very nice. What is I? Isolation. Yes. As if all the others in the world don't matter, all by yourself. It's actually isolation, okay? Integrity sounds pretty nice. Okay, all these together, acid actually gives you integrity, so that's not a separate I. What does D stand for?
Durability.
Yes. So D means permanent. So once all these happen correctly, your data is safely saved forever in the permanent storage. It takes a lot to undo it, okay? Yeah. So these four are very cool. Right now, the only thing I talked about is atomicity, which comes from the whole transaction processing. It tells you if a part of a transaction fails, we'll make sure the whole thing fails. Okay. And then we use logs to guarantee that. That's basically the bottom line. So now we'll actually go for a few more minutes. We can take a little break. All right, so again, a transaction is just simply a whole bunch of SQL statements, okay? Usually things like update, insert, you can even have delete in there, but it's more than one usually, and it's a transaction together. So they all have to succeed or they'll have to fail. Update is usually the main thing you look for because it's modifying data. Again, in update, I take money from one table, I update another table with money put into the table. Both updates should work. Only one update cannot just work and fail in the middle. Even Amazon, again, once they accept the order and after they accept it, say they're not able to find like a shipper or for any reason, they might actually decline your offer once in a while and say, sorry, your purchase failed, So that's again the same reason you don't want to be stuck with some fake transaction. All right, so the whole transaction leaving the database in a consistent state that matters. We assume that before your transaction even came along, the database, the collection of all the tables, all the data was perfect, nothing was bad. There was no corrupt data anywhere. And therefore, then the system expects your transaction to then leave the database in the same consistent state. In other words, a transaction will take the database from one consistent state to another consistent state. It means the transaction itself will not make the whole database inconsistent. That's a nice thing, right? It's a nice property. That's what the whole atomicity is, because it's all about consistency. So like this, you begin with the consistent state, end with the consistent state, okay? Otherwise, the transaction is bad and we throw it away. All right, so our database request is a single SQL statement. So request is things like, again, I'm reading some data, I'm buying something, I'm updating some value, I'm modifying the GPA, I'm signing up for a course, I'm dropping a course. All of those are like requests. In the end, your request turn into like a bunch of SQL statements, more than one SQL statement. It's all the same thing over and over, okay, many different words for it. So in the end, the transaction is more than your one SQL statement, and you want them all to run. Okay, so then how does it work? Acid is right here. Maybe we can take a break after acid. That's funny. All right, so you can read a Wikipedia article on acid. There's like too much written on all this, okay, like 30 years worth. So I don't need to repeat all that. And you can just know, this all, by the way, done in every single real database in the world. The Amazon example I showed you, right? MariaDB and, like all of this, right? Postgres, MySQL, what. All of those already do all of this ironclad. So it's not that you're learning anything new that people don't know about. It's more like FYI. So don't worry about too much about all this, okay? It's FYI. It's nice to know, and I'll tell you enough that I think you should know. But beyond that, don't be obsessed with like knowing every possible little piece of it. It's too much. Okay, so what is acid? Atomicity is, like we just now said, all the operations, because it's more than one, in a transaction must be completed or not. If it fails in the middle, then the ones that succeeded would be rolled back so that it looks like nothing happened. You never even tried in the first place. Try again later is what it means. So consistency is, again, this is what atomicity is all about. You have to leave it in consistent state. So consistency means the database is always guaranteed to be in a consistent state. That's how much like a separate guarantee. Nothing will ever make it inconsistent, including bad transactions. Isolation, this is again where the concurrent people come in. So in reality, many people are operating on the same Amazon database, on the same, practically anything in the world. New concert is announced, okay, a new product goes on sale, a new iPhone comes out. There's way too many people all want the same thing. And you an eBay auction, right? So many people are watching it. Somebody's bidding on it, only one person at a time. So in reality, all transactions are concurrent. Maybe at the micro, nanosecond level, maybe not. But in reality, we're all doing the same thing at the same time. But from the database's conceptual point of view, the transactions can all be ordered. In reality, along time, they're interleaved. Okay, I'll tell you something right here. There's something called a serial schedule versus a serializable schedule. A very big difference between them, okay? A serial schedule means time always goes this way. I do all my things to the Amazon database, all my things, anything that I ever want to buy, sell, do product trading, ask questions. But the entire world is shut out. I'm the only one in the world ever using the Amazon database. Just imagine if that's true, okay? And then you come along, so I'm done. Then I leave, and you come along, you have the entire Amazon database all to yourself. The third person comes all to yourself. If that is possible, right? Say I'm called T1. All my reads and writes are all T1 something, T1, all T1. Somebody else is all T2 transactions, somebody's T3. They're strictly blocks, blocks, blocks. That is called a serial schedule. So serial literally means one at a time. So schedule. But this is the most wasteful thing in the world, because Amazon won't be Amazon, okay? If I make everybody else in the world wait, they're going to Alibaba, right? So it's not real, okay? But conceptually, it is possible to imagine that. That is called a serial schedule. It's not practical in the real world at all. In the real world, what is happening is, say T2 has this different color, right? So T1 was already that purple color. So then a T2 can happen. T2 can happen here. T2 can happen here. T2 can happen here. And say T3 was a different color. And then T3 can also go here. They can go here. They can go here. They can go here. They can go here. This is the real world. If a database system can make this happen and still come out right, in other words, if you look at the end result, it's as if this happened, as if this happened, as if this happened one at a time. But in reality, all happening at the same time. Such a concurrency is called a serializable, sorry about the writing, okay? Serializable schedule. So serializable means it is possible if I want to pull it up. Okay, so that guarantee is actually very cool. That's called the isolation property. See, in reality, you're not isolated because it's pretty inefficient. You're locking the whole database out. But you don't have to lock it, but still have the same guarantee by mathematically analyzing and reordering your transactions so that it comes out as if it's serial. Then that property is called serializable. Whoa. Okay. So 742. Should we stop? Well, we'll stop after this. So then the thing that so these are related, obviously. So isolation means this is all about locking. So how do you ensure serializability in the real world, even though they're all like interleaved? When it's your turn to write, everybody else would have to wait for just a little piece of time that you're actually writing. So that's called isolation. So it's as if your transaction is really isolated. In other words, all the writes are isolated so that nobody else can come and do the exact same write. They have to wait. You have a lock basically, okay? So until your lock is released, they have to wait. But not a lock for all the things that you do, meaning not all the read locks, other people have to wait. Read locks can be shared, but only writes other people have to wait. That's isolation. But isolation is tied to this idea called serializability, because what isolation actually meant when you were writing is it's as if you really had the whole table to yourself. That is called serializability. So these are all, as you can see, highly interrelated, okay? In the end, all of those, even isolation, even serializability, even atomicity, is actually all about one thing. So in ACID, C really is the most important thing. Your database cannot really have bad data for any reason. Like I do a transaction, your transaction should not come and overwrite my transaction. That's bad data. So all these other things really exist only in the service of consistency. That is why many people won't even talk about S as a separate guarantee. People just talk with ACID. D is something very different from all this. D just means if all this works correctly and my transaction, all the transactions happen perfectly, then we'll commit all that to permanent storage. So it becomes pretty hard to undo. It literally just is forever. And you have to go through a special rolling, unrolling process, look at the log files, and then put the data back manually, really using more SQL to reverse what you did. It's not easy just to undo. And that should be a good guarantee, right? It should not be that easy to throw away like massive changes people made. That is called durability. So many books and many people only talk about the ACID guarantee, but sometimes you call it the ACIDs guarantee. Our book actually talks about serializability. But to me, that is actually heavily tied to isolation. So in a way, I would subsume S in I and throw S away. But you get the idea, right? Okay, wow. So why don't we stop? Should stop. And then maybe come back at 7:54. Amazon would lock only for, yeah, absolutely. That is exactly right. Yeah, you will actually see it even when you buy like a movie ticket or anything, right? There's literally a clock, a little rundown clock that says only for a little while we lock you. Yeah. They might not even tell you that your lock is gone, but after a while your transaction is basically not happening, because cells can only be locked one at a time. Yeah. All right, so let's come back at now 7:55. Bye. Hey, cool. Continue. You guys still there? Can you hear me? Oh, cool. Okay, thanks. I like all the confirmation. So I pulled up a few things just to show you, right, in relation to what we're talking about. So one of them is actually this one. So this one more SQL thing that is highly worth watching for just like less than 1 minute, okay? But watch this. So natural language query to SQL, a different demo. So now they're going to start typing. Okay, so this is, basically something that we saw before, right? But then this can keep going and the queries get more and more complex. So at that point, it's not just trivial, select something from something, where something. See, that's neat, right? So in other words, what happened was, fairly miraculous because in the past, there was no other way that somebody could read that and actually write that in just like a few seconds, right? And it only gets better and better and better. So the more training data that we have, in other words, more complex SQL queries we have available, then we can describe that to the system and the system understands. Oh, I see. Yeah, I'm going to fix it. I'll definitely fix the link for sure. I'll find something even longer, okay? So I'll definitely fix the link for this. Yeah, but the idea was, this is actually very interesting because it's an inner query. And so, it just simply pulled it up. And so it's a matter of us humans making the system more like intelligent, and then it will actually get there. Then in the meanwhile, I wanted to show you how complicated, this whole airline booking thing is, right? Because it's actually, as you know, the main complication comes from the fact that you have now so many apps, that you can download, right? And then so many sites you can go to, anything from Travelocity to just on and on and on. Sabre booking systems, there are too many databases. So if you start reading how complex it is, global distribution system, this is what all airlines ultimately share in terms of what seats, what airlines, what country. It's a global database. It's called GDS. But the GDS is now accessible in so many multitudes of ways. So when I say 100 people are trying to buy your seats, the 100 people not even use the same app. They're using God knows what, but so many different ways in which it's possible to get the same data. So there's APIs for them, okay? So if you like API programming, there's massive amounts of APIs that all just give you just the airline booking information. Wow, look at it. There's so many. And then if you're fascinated, you can read about all this. So all the systems, right? It almost looks like Python, but it's Python. So they can all be used, to buy tickets. And so that's what all of this is. See? So there's too many APIs because it can all tap into the same database. Sabre is one of the biggest ones. In the past, only travel agents used to have specialized applications that would be locked into all these APIs. But now you and I can make a little query and actually get data. Yeah, that's interesting, wow, at the same time. I don't know why you tried that, but that's a fascinating test. It tells you that not all APIs are the same because look at how many there are, right? Some of them are probably slow and buggy even. That's terrible. The airlines API is buggy because you're going to lose seats, But then all this just points to the central idea that I was trying to tell you, which is the resource is pretty scarce. There's only so many seats going to a foreign country. And, basically tens of thousands of people want to go, but not everyone can go. And so how do you manage it? So the last thing you want is disappointment. Everybody showing up at the same time, thinking they're going home and getting horribly angry, right? Or many people buying books and then just being told after 1 week, sorry, you have to wait for 2 more months. Then they could have bought it somewhere else if they knew ahead of time. So it goes back to the same problem, same issue, which is concurrency transaction management. And it's very simple. So I'm going to start by telling you like how simple it is. So we looked at ACID and then this notion of commit. Yes, a commit and rollback. We've dealt with this before, but now what we can say is a little more, which is when a transaction naturally completes. A transaction is more than one SQL statement. If you reach the end of all the SQL statements properly, meaning the atomicity was not broken, then automatically a commit is issued by the system. So you don't have to type the word commit. So every successful transaction is automatically committed. I see. Yeah. Wow. Yeah. Payment APIs are also highly varied. How quickly can you validate the card? If you lose out, then you can lose the ticket. Because again, that is where the atomicity comes in. They cannot give you a ticket and then find out that your credit card was fake, okay? That's pretty bad. So then they have to reject you, so then those things. Okay, so commit, naturally, at the end of a transaction, commit can happen. On the other hand, if a transaction was quite large, in the middle of that whole large transaction, you can actually insert the word commit, and then a part of the transaction could be committed. So it's entirely up to you. Roll back, like I said again, if the program is abnormally terminated, then you can do a rollback. Or manually, you can always do a rollback anytime. Suppose you when the transaction appears to go properly, you're doing it piece by piece. You can always roll back manually, meaning these statements you can insert yourself, but in reality, they can automatically be done by the system. That's all it is. You can book a ticket. I see. Yeah, in that case, they did not quite update the count. See, that's also possible, by the way. The actual count that tells you how many seats are left. It is not always in real time being updated. Yeah, that is true. This is what I mentioned a little while ago. If they do it on purpose, that's actually pretty bad. They're willing to lose some money by doing that. It's weird. Okay, so therefore commit and rollback, not much to say, but otherwise just tell yourself naturally if a transaction succeeds, it'll be committed. It'll naturally be rolled back if it is aborted. You don't have to manually worry about aborting. You don't even know that it got aborted. They'll just tell you, sorry, your whole thing failed. Sorry, your update. You go in your bank ATM machine. Sorry, your transaction failed is all they tell you. No reason saying, oh, this got stuck here. Okay, updates. I'm going to show you some slides and then we can maybe stop after that. That tells you how, like what the problems are, like what happens if you don't do it right, okay? And these are highly just FYI, meaning this never happens in the real world. Even if you try, it won't happen in the real world. But then the question is what can happen? Like 3 different scenarios I'm going to show you. And there are 2 more scenarios that I'll just name, and your exercise is to, just Google them and look for them, right? One called phantom reads, okay? So what is a phantom read? It's basically an update problem. But I won't tell you what it is, you can read it. And also tell yourself in the real world, phantom reads never happen. All right, so then what could they be? In the meanwhile, this very all important, simple file called a transaction log is what really saves your butt, so to speak. So how does the rollback magically know what to roll back? In other words, who is recording all the partial transactions as they're happening in case you need to go back? The answer is a very simple log file with a timestamp. Every time a transaction happens, right? I'm going to show you the log file is right here. Is you make an entry, you make 1 row of data, and you put the timestamp, like exactly what time the transaction happened, what table the transaction is about, what cell, meaning what column, and in the column, 2 values. What was the before value, what was the after value? Meaning I changed something to something. I changed your GPA from 3.8 to 3.87 because you thought that you'd get a better grade. You asked your professor, you got better grade. Then we store both the before value and after value in the log, literally just store them next to each other. So like this value, before value, after. I'm going to zoom in on it in a minute. So that is really what just happens for every transaction, a before, after, before, after. If you ever want to go back, take the after value and then basically throw it away and replace with the before value. It was 25. 25 got overwritten with 23 somewhere else. In a cell, there was the number 25. You overwrite that with 23. So now 25 becomes the before value, 23 becomes the after value. So you write that here on a separate log. So in case that needs to be rolled back, how do you undo? How can you make the 23 go back to 25? The value is gone, but it's not gone, it's over here. So copy this value over here, become 25. So a log is that simple, but it's so important, okay? This little thing. Then the question is, what happens if the log writing gets corrupted? Well, then you're in very serious trouble. So this thing, somebody at some point the bug stops here. So we hope that the log is highly durable, the log is on a very good mission and so on. But a log is exactly this. So transaction ID, because the same transaction can actually have many log entries. The log entries don't even have to actually be sequential. So this is a transaction ID, meaning your transaction, somebody else's transaction, what. So 101, 102, 103, they can all be interleaved, okay? This one is more like row ID. So in here, there's a transaction log ID. So this is where amazingly you can have a before and after. If a transaction called 101 starts for the very first time, there's no, exactly, so you can access the log file, yes. So there's no transaction ever before literally the start. So this is like a doubly linked list is what it is, okay? So the previous pointer is pointing to null, the doubly linked list. So my one transaction happens, it's not even a real transaction. It's a mark of a transaction, just start. Okay, start things off. After that, my 101 does something, okay? My 101 is gonna update the product table for the product. Quantity on hand went from 25 to 23. It means somebody walked in the hardware store and bought 2 of these, okay? That is my next transaction. But for the next transaction, the log file says this. I'm still part of the same 101. I'm not done yet, but my previous pointer is 341 because it is literally the previous value. And then I'm not done yet. My customer balance, so I have a card, with the Meets Home Depot. So I have a Home Depot credit card. Then they have to update the credit card value. So then my balance went from that value to that value because I bought like $90 worth of stuff. And so that has to be recorded, still part of the same transaction. So that gets its own row ID, but the row says I'm pointing back to a previous row. See how cool this is, right? Likewise, you can now have a next ID. So this row over here has a next called, so the previous pointer was 341, and the next pointer is 363. Then likewise for that one, the previous pointer was 352, next pointer is 365. When you commit, so this means I'm going home with my product and I'm all done. So that is one log. But in reality, while this is happening, somebody could have inserted their row ID as a start. That is totally okay, all right? But the log knows whose transaction is what. Therefore, it'll keep all the transactions, even though they're physically separate. In the end, they're all easily traceable because of a log is what we're saying. Okay, so as far as just one person's transaction is concerned, it's a doubly linked list, okay? So on the one hand, you're pointing to all the forward transactions that all happen. On the other hand, you're also pointing to all the backward transactions. Even though in time, somebody else could have done something and they have their own double loop going, okay? So that is all totally possible. So at time-wise, T1, T2, T3, what. But in reality, they're all serializable because it can all be done separately. Okay, so in the log, you can pull them out, which is why you have the transaction ID in the log. Yeah, the log can be accessed. The log will be accessed when it has to be aborted. Scroll back. Okay, cool. So given that, what can we do is the question. Okay, so how can we demonstrate some neat things about this? Okay. Concurrency is many at once. So we said this already, but we can say it again. In reality today, because we're internet, practically everything that you ever do, even LinkedIn, you're looking at people's resumes. You guys apply for jobs all the time, okay? It's the exact same thing. It's not that jobs are gone, but it's more like, they keep track of how many people are looking at it, how many people are applying. Those numbers are locked when you actually put in your resume and say apply for this job. There's some cell that is locked that says how many applicants do we have. Okay, so it is concurrent after all. All right, so concurrency control is somehow making sure that all the simultaneous, nearly simultaneous, meaning they are ordered in time after all, within like milliseconds, execute properly in a multi-user. The whole world uses multi-user databases. Objective is to ensure serializability. So it means they're not really serial, like you don't do them separately, but they should be serializable. Then you're fine. If it is not serializable, it means something is wrong. So this means there's some deadlock. It means people are waiting on each other. And the two transactions that are like waiting on each other cannot both work at all because they'll permanently wait forever. And so you have to actually break one of them. That's called deadlock breaking. So the whole deadlock stuff, okay? It's all tied to serialization. Okay, but in the meanwhile, I'll show you 3 problems. That's probably all we have time for. All right, so if things don't work properly, meaning we don't lock, basically. Suppose cells are not locked, okay? Then what can happen? Okay, so in good old GitHub, before GitHub, there would be a repository. So 20 years, 30 years ago, we had a repository, but no GitHub, it's called a repo. The repo is a centrally located bunch of directories where some critical files belonging to DreamWorks. This is the rendering program for DreamWorks. It renders Shrek and all the cool movies. All the source code is kept here. Sati is sitting here. And his colleague Gigi is sitting over here. So then Sati checks out a file, something where there was a pointer bug, so it is leaking memory. And Gigi also checks out the same file. She's trying to fix some other part, of the file. It's a different problem. Maybe the help string is not working properly. So I do my bug fix, carefully do all the memory allocation, and then I check it back in, get some confirmation. Then Gigi does her fix, and then she checks back this exact same file name. So then my changes got completely overwritten by her changes, meaning, yeah, she helped she fixed the help string, but then the memory bug that was in her copy is gone back here. So my fix is basically trashed. You understand, right? In other words, her changes overwrote my changes, and that's a very bad thing. So there's 2 ways to lock in the past. There was one called revision control system. These days we have Git. Before Git, if you are a little bit older, you had things like SVN, for example, things like Tortoise SVN. You remember SVNs? It's SVN. This is an internet way of doing distributed check-in, check-out. And before internet SVN, Tortoise, GitHub, all that came along, there was 2 different big ones called CVS, not the drugstore, but versioning system, or RCS. RCS stands for Revision Control System, where what we just said is not possible. In CVS, what I said is possible, concurrent revision system. Since CVS, when you check something out, it is not locking anything at all. Okay, that's not locked at all. So anybody can check out anything and potentially override each other. It's a very crazy way it works. but then it makes many people work on the same file at the same time, if you want. Then they all have to somehow merge the changes together. On the other hand, RCS is much more pessimistic, okay? RCS is very careful about locking. So this will lock. So when I check it out, that file is locked. So Gigi could not have gotten her own copy. She has to wait, okay? So that is what we're talking about. The whole locking matters in software development. So in GitHub, very similar. When you all can do, your own multiple changes, you do what's called a pull request, meaning you cannot just go and update the master. You need to tell the owners, I made some changes, please take it and see if it is okay. Then that person manually can merge all the changes in. Otherwise, the same problem that I mentioned would happen where I check out like a piece of repo, you also check out the same repo, and then I fixed afterwards, you fix, then your fix is overwrite my fix. So in GitHub, we prevent that by using the whole pull mechanism, okay? But it's still a problem. Nobody fixes it. Okay, so then that is the same problem that happens over and over. Okay, the first problem is exactly what I mentioned just now. It is called the lost update problem, where one transaction goes and makes a change to a cell. And then a few seconds afterwards, a different transaction comes and overwrites the previous change. So the previous change is gone forever. That is called a lost update problem. I have like some nice little things to show you, but just verbally, here are the three. So you can read it yourself if you want. Yeah. So the second one is called uncommitted data. So this notion of committing, right? Committing means my transaction, happened properly. I've made all the changes and then it's committed so others can come and get my data. But in the middle of me doing my transaction, I'm allowed to go back. I'm allowed to roll back. I made a mistake and I can fix the cell, right? That's all not your business. I'm still operating. You're supposed to wait outside the house. But say you come in and while I'm making changes, back and forth and modifying data, putting it back, what, you read some value, then it's your fault because you probably write a bad value in the sense that I threw the change that I made away because I didn't mean to make the change, but you took it. So you took a bad value because you did not wait for me to commit. We're changing all the time, but that's okay. I'm allowed to do it. But you came along and took the changes while they were being changed. So you probably got bad data. That is called uncommitted data. It's called uncommitted read. The reading uncommitted data. You cannot write, by the way, when I'm writing. It's not that bad, although that happened here. So here you're reading the data that I'm changing constantly, so you don't have the latest value. So very similar to that is this one. So inconsistent retrieval is again, these are similar but different, okay? In here also, same problem, which is I'm still not done, but you came and took it in the meanwhile. In other words, I'm modifying data and you're trying to sum up all the columns, that I'm modifying. So you're going to get wrong total. So I'm going to show you all these three, okay? Okay, and then we can stop. All right, so this is very easy. There are only two transactions easy. And we call them T1 and T2, okay? So T1 is like a purchasing manager. So you're in the back of the store, the hardware store, and you're ordering 100 items. So T1's job is to take the quantity on hand for some object and add 100 to it. And you don't know what is happening elsewhere. T2 is the point of sale terminal in the front of the building. I'm checking something out. So that's T2. So this means the customers like bought 30 cans of paint, for example. So then that's like minus 30. So the question is, if you do T1 first followed by T2, things will work properly. It's a purely serial schedule. So you're supposed to get the right answer. So what is happening is only 35 units of the paint cans were left. So the manager orders 100 more. Then the inventory shows that 135 objects exist. Then I come along and I buy 30 cans of paint. So 135 minus 30 is 105. So remember that this is the right value when you compare with what happened. Okay, what's going to happen is we'll not see 105. We'll see everything but 105. But if things happen one at a time, like, you did your purchase in the morning, your update in the morning, and I came and bought the paint cans in the afternoon, we really have nothing to do with each other. So that's the easy case, okay? Most likely that's not what's happening. So then how can that go wrong, okay? Okay, so serial schedule, it can never go wrong because it's only one at a time. It's pretty easy. But the errors happen when you have not serial. So first of all, time is running vertical. You can look at that. And T1, T2 are interleaved. That means they're like mixed together. T1, T2, T1, T2, T1, T2. But what happened at the very end? 5. What the hell? How did we get from 105 to 5? Because here's what happened. It's a pretty easy thing that happened. So again, you're like here. So T1 is reading the 35 because it wants to place an order. Meanwhile, the point of sale terminal is also reading 35, reading it almost at the same time, okay? Like a few milliseconds apart. So you think it is 35. I also think it is 35. You order 100 cans of paint. So now in your mind, there's 135 left. But I, going from the same 35, subtract 30, So I think that 5 is left. Okay. So you ordered, I bought, but we're operating off of the same number. That's the problem. Then here's where the last update comes in. So T1 comes and says, wow, let's show the whole world that we have 135. Then T2 says, let's show the world that we have 5 left. See, the problem started when we both read at the same time, okay? So your 135 got overwritten with my 5. That is why we end up with 5. Wow, right? Last update. Yeah. So it's a real problem that, can happen, but, obviously, hopefully not, is what I'm going to say. So our update comes out to 5 instead of 105, because literally your 135, see, look on the right-hand side. So the 135 got instantly, pretty soon, got overwritten with my 5, because the problem was that we both, read at the same time. Like the transactions were not, like in other words, I did not wait for your 135 to be written. The write was not locked. So therefore, I could come and override it. All right, that's like lost update. Like your update was lost because of me. T1 was lost because of T2. Now let's do rollback, okay? So now what happens is, suppose you, T1 comes and buys 100 units. And then T2 is now, buying 30. But the thing that T1 ordered the 100, they ordered the wrong kind. And so then it's not really 135. Say it was 35 earlier. It's not supposed to be 135. It's supposed to go back to 35 because I'm deciding to change my mind. Sorry, I should not have ordered, so you ordered somebody else. In the meanwhile, you read my wrong total. So now you're going to leave the store with more than before, okay? Instead of 5, we're actually going to have like 105. It's opposite problem. So then if you do it correctly, sequentially, then the purchasing manager says, oops, I made a mistake. So they went from 35 to 135, then went back to 35. Then you come along and that's the correct number and you buy 30 and you're back to 5. So 5 is the correct total again, right? Like we had before. But what if you did not wait and you're left with the wrong value? Instead of 5, now we have 105 because I read and I'm ordering and I'm like, oopsie. Then I, try to, put it back. But before I could put it back, you read the wrong value. You read the inflated value and you subtract 30. So I put it back and I make it right. You put it back and screw it up. So these are fascinating cases, right? Imagine instead of 2,000, okay? It's the reality. See, if these things are not managed properly, all hell would break loose. So even with 2 cases, okay? 2 different problems. And I show you a third problem, then we stop. All right. So then in this case, again, it was all because you're trying to fix. So previously, say you order the wrong product. Then this is the third case. T1 transaction's job is simply to sum every single product quantity on hand. I want to know all the products across the whole store. How many things do I have? 10,000 objects, I want to store that. That's my T1. Meanwhile, T2 is doing this. T2 says, update the product so that this product code that I really should have bought, add 10 to it. And the product code that I bought by mistake, subtract 10 from it, okay? So in the end, nothing really changes in the sense that this one is now put back. Previously, this had an artificially inflated number. I ordered 10 by mistake over here. So like this 10 I ordered over here. So now I'm fixing the problem by taking 10 away and putting it back to what it was and increasing this by 10, which is what I should have done. So remember, the good product is QQ2, the bad, like QQ. The bad product is QW1, okay? Just remember that. Okay, so once again, if you do it one after the other, there's no problem at all. Okay, so if you properly do it, so 92 is the right number, okay? So then say this is the cumulative value. So you're just adding like all the values. Then this is how it used to be. So 8, 8, 32, 32. And then QQ2, remember, this is the one that we ordered incorrectly. So I have 25. And then QW1, then is that correct? QQ, no, I got confused. This is the one that you want, sorry. So QQ2 is the one that you want. QW1 is the one you don't want. That's what we do here. So QQ2 is being put back correctly. Yeah. Okay. So that is being put back correctly. And likewise, this is being undone. Okay. So I put it back. Then the proper value, after I do all of this, if somebody goes and adds this, they should get 92. Okay. So remember 92. But meanwhile, this is what's actually happening. Say T1 that is trying to add everybody does this. Okay. So 8, 8 initially, cumulative total goes away. So then 8 plus 32 is 40, then 15, you're not. So 15 is when something is happening. Okay, so 15 is being added by 10, and that is the correct value. You want to go from 15 to 25. But 23 should have been 13, right? So in the middle of me doing 23 to 13, this thing that is adding everybody did not wait for me to do 13. Instead, it read 23. It read the 10 values more because it read the bad value as opposed to the good value. So therefore, it got 10 more than it should. And then overall, it ends up with 102 instead of 92. Right? So the mistake was here. This was fine. The mistake was it read the before value rather than the after value. Yes, thank you. I'm going to stop. So it's actually 8:21. Yeah, so in the end, we'll just stop right here. Okay, so what we're saying is if you're able to lock, then you're going to get the right value. On the other hand, if you don't lock and you let things interleave, then bad things will happen. So we should just stop right here. This last thing was called dirty read. It's reading dirty data. So please also look up the fourth kind and the fifth kind of bad reads, okay? So the reads are like a big problem if you don't lock. And then next time we're going to continue from here. All right. I want to stop so that they can set up for the next class, okay? Goodbye, everybody. Bye. You're welcome. I'll read some names until they just shut it off. Vaishnavi, Malaki, Karthik, yeah, Isha, Vignesh, Kishan, Surabhi, Kristen Mills. Bye-bye. Sweetheart. Kenneth, shit. Fang. You are all welcome. Akshata, Atashri, Garima, Hamza, Miss Petroleum Engineer. All right, thanks and good night. Goodbye, everybody.